Hello, hello.
Hi, Bryant.
Hi, how are you? Are you feeling better for this midterm two coming up?
Oh wait, maybe my headphones are tweaking.
Oh,
Give me a sec.
true. Uh-huh. Yeah. So we could do this review session in a couple ways. We could go over the practice worksheet that I sent out earlier, like in the Discord, or we could do a Q&A session, or we could go over the two winter 2023 midterm two sections, and I teach you guys the concepts as we go over those problems.
Hello?
Hello,
Can you hear
hello.
me?
Yeah, I can hear you. Can you hear me?
I don't know what happened. I don't know if you heard me or not.
Yeah, I can hear you. Can you hear me? Wait, can you guys hear me? Oh my gosh, is it me? Um, Hello. Okay, okay, okay. That's good. That's good. Okay, yeah, let's go over the mechanisms in my practice. And then we'll do some practice synthesis, some practice midterm questions. Let's do it. Okay. Uh-huh. Let's go. Okay, so here are the predicted products. Let's do the mechanisms of these. And after these, we could work on the synthesis problems because after we go over these, you guys will like be familiar with the pattern recognition, be familiar with each reaction's transformations, and then you guys will be prepared for the synthesis problems. Okay, so we have an alkene right here reacting with first step Br2CCl4, second step NaNH2, two equivalents, and NH3 liquid ammonia. So the first reaction here is gonna be an alkene reaction. Do you guys remember what the mechanism would look like? Like, what is the special intermediate name when we react an alkene with X2 in a product CCl4 solvent here? Yes, so the product will be a vicinal dihalide. So if we do the first reaction, we are going to get this vicinal dihalide here, where the two halogens, in this case, the two bromines, are vicinal to each other, adjacent to each other like that. Right. Okay. So now we have two good leaving group presents here, and we have NaNH2, NH3 liquid. When you see Na, always associate that with a positive charge. That means that whatever is negative charge, like charge is next to it, is NH2 minus. And NH2 minus here is a small, strong base. So if it's a small, strong base, think of Zaitsev E2 reaction, right? So if we're gonna do Zaitsev E2 reaction, I'm gonna do it two times. Let's say we grab this hydrogen, create a double bond
We
there,
started.
kick out the leaving group, and we're going to
What if you're unmuted?
create that alkene right there with the bromine. And that was the first equivalent of the NH2 minus strong base, right? We could bring in a second equivalent of NH2 strong base because we have two equivalents there to do another E2 reaction to create another pi bond. So we're gonna attack that H, make that extra pi bond right there and kick out the leaving group, right? And that's gonna create the alkyne. Now be careful here, right? What is the geometry of an alkyne, a triple bond? Like, what is the preferred bond angle between them? Is it 109.5 degrees, 120 degrees, 180 degrees? What is the preferred bond angle for triple bonds, alkynes? From Gen Chem? 180 degrees, right? So it has to be linear. So draw your alkyne like this, okay? And don't draw like this because this is cursed right here, right? That is not very good. Yes, that. And to keep track of your atoms, like some people add extra carbons by accident, some people add like remove a carbon by accident. You could like number them. Like you could number them um 1, 2, 3, 4, 5, 6, 7. And to make sure we have the right number of carbons, we could say that's 1, 2, 3, 4, 5, 6, 7. And between 5 and 6, that was the vicinal dihalide, right? 5 and 6, which is our internal alkyne, the alkyne inside of the molecule. Okay. Any questions on this mechanism problem? Predict the product problem before we move on to the next one?
Actually, had a question.
Yes.
Does the PR minus always attack on the more substituted in order to make it trans? Like the BRs have to be trans to each other, right?
Yes, the BRs here, they have to be trans to each other because this halogenation reaction is anti-addition. They have to be
Okay, got
trans
it. Thank you.
to each other, right? So if this was a wedge, this would have to be a dash, and vice versa. If this was a dash, that would be a wedge. But I didn't draw out the wedge and dashes here because our final products here, those carbons would not have any wedges or dashes at all, right? But that's right, because keep that in mind. Like, still remember the regiochemistry of the reactions here. Halogenation is anti-addition.
Got it. Thank you so much, Brian.
Yeah, of course, Khadija. Okay, so let's do the second reaction here. We have a good leaving group, and we have a multi-step predicted product synthesis. We have a first step with a bulky base, which is going to do E2 Hoffman. We're going to grab the less substituted hydrogen. The bond between this hydrogen being grabbed and carbon right there, that bond is going to go make a double bond right here, kick out that leaving group to create the less substituted alkene. Right there. Right? Now, once we have this less substituted alkene, we're going to do the same reaction as we did previously, halogenation. Make a vicinal dihalide, 1 chlorine for each carbon of the alkene, here and here. Now, we have 3 equivalent of NaNH2 now. So let's do this mechanism again. Let's use the first equivalent to grab that hydrogen, create a pi bond there, kick out the leaving group to give us this alkene. Use the second equivalent of strong base to grab that other beta hydrogen, create that alkene, kick out the chlorine leaving group to create this alkyne. Now, this is a terminal alkyne, where it is at the terminal end of the molecule. If this was a synthesis problem, you cannot use 2 equivalent of NH2 minus. You need at least 3 equivalent of NH2 minus, because this right here would actually be in poor yield, low yield. To get this in high yield, we would have to deprotonate this acidic hydrogen right here. The reason why this hydrogen here is acidic is because of this sp carbon right there. Right? If we were to deprotonate with a base, that carbon would be stabilized by the sp hybridized carbon. Right? Yeah. If you don't include 3 equivalents, you could also say excess, right? You would have to either put excess or 3 equivalent. If you just like put NH2, then that's going to be assumed 1 equivalent for synthesis, unfortunately. Right. X2 addition to an alkyne does not use CCl4, right? So X2 addition to alkyne can use CCl4 or water, and we'll go over that reaction later. That reaction is going to be later. We'll go over that reaction later, Emily. Why do we need NH3 liquid? What is its use? So NH3 liquid is a solvent of the reaction. It would like allow for these ions, sodium ion and NH2 minus ion, to exist and float around in, right? Because ions cannot just like float out in a non-aqueous solution. Because like, let's say there was no aqueous solvent there, those ions would be like table salt, like NaCl, it would be solid, right? But we need like some kind of aqueous solvent for those ions to float around. So they give it like NaOH and water. The important thing here is the OH minus. The water is just a solvent, and we could ignore that for mechanism, right? The third equivalent of the NH2 minus here is going to deprotonate that terminal alkyne hydrogen to give us this alkynyl anion here, that's negative charge. Once we have that negative charge right here, then we wait for a while in lab to get this in high yield, And then once we get that in high yield, we then bring in the fourth step, the very last step, acid workup, to protonate and neutralize the negatively charged alkynyl anion to get the terminal alkyne right here. Like that, okay? For an internal alkyne forming, do we just not need the third equivalent and acid workup because there is no hydrogen to deprotonate on the internal alkyne? Yeah, that's correct. For an internal alkyne right here, these sp carbons are not acidic because there are no protons attached to those internal carbons. Whereas a terminal alkyne here does have an acidic hydrogen on an sp carbon right there, right? Which when it gets formed in the first place is in low yield, poor yield. If we want in high yield, we first have to like deprotonate all of those hydrogens into this alkynyl anion, wait for a while. Once we get this in high yield, we then dump in acid to get our neutral desired terminal alkyne. So just to be clear, when writing out NH2 for synthesis alkyne, synthesizing alkyne, we have to put NH3. So for synthesis balance, you don't have to put NH3. You'll probably get full credit if you put NaNH2 excess, right? To be safe, for both internal and terminal alkyne, you could put excess NH2 minus, and you get full credit for that, right? Because excess would like, you know, cover 2 EQ and 3 EQ if you don't want to like memorize that. And predict the product, he will give you the 2 EQ or the 3 EQ. Right, but if you're doing this in synthesis, you don't have to put the NH3 liquid ammonia, right? You can if you want to, but you don't have to. Yeah. Okay. If you said 4 EQ, that would be okay. Yeah, that would be okay. 4 EQ would be okay. Yeah. Okay. But then make sure, like at the very, very last step, you put acid workup in to protonate everything. Okay. Yeah, you can put like 100
Sophia,
EQ.
my tutor's having a review session right now. If you want to join, I can send you the link.
Yeah, we could put like 100 EQ, 1000 EQ, 2000 EQ, over 9000 EQ. Okay. Any questions on this one before we move on to the next one? Okay, let's move on to the next one. Right, before we move on to the next one, I want to show you guys this chart really quick with the alkynyl anion reactions that Helix wants you guys to know. And there's 3 of them. So let's say we have this terminal alkyne right here, and let's say we deprotonate it with one of these bases. He gave you 4 bases that you need to know to deprotonate the terminal alkyne. The most common one is NaNH2, right? Specifically the NH2 minus. You could use NaH, where you have a hydride ion to deprotonate it. You could have LDA, or you could have N-butyl lithium, like that, right? Where the base is that negatively charged carbon right there. NaOH is not acidic, not basic enough to deprotonate the terminal alkyne hydrogen, right? So let's say we use one of those 4 bases, NH2 minus, or H minus, or LDA, or N-butyl lithium, to deprotonate that terminal alkyne and get this alkynyl anion here. Right, this alkynyl anion, the negative charge on this carbon right here, can act as a nucleophile or a base, depending on what reagent we give it. What about for internal alkyne? Would NaOH be acceptable? Internal alkyne. So if you want to like form an internal alkyne, then you could use NaOH as the base, right? But I wouldn't use NaOH. I would use NaNH2 because for an internal alkyne, there is a chance of, you know, like let's say we have this vicinal dihalide and we put OH minus. This right here is like a primary substrate, which can do SN2 here, but I guess it would work because like this is a primary hindrance substrate. So, this is an internal alkyne. Yeah, Yeah, if this was an internal alkyne, you could use OH minus as a base to make the alkyne. But the bases that I'm talking about here are going to deprotonate that terminal alkyne hydrogen to give this sp carbon a negative charge, right? Those 4 bases right there are able to deprotonate this terminal alkyne hydrogen, right? Which gives this carbon a negative charge and can act as either a nucleophile or base depending on what reagent we give it. And you need to know 3 of them: a primary haloalkane, secondary haloalkane, and epoxide with an acid workup, right? So examples here. Like that, right? So let's say this is reaction 1, reaction 2, reaction 3. Reaction 1. Let's bring in that alkynyl anion with this primary haloalkane. This is our nucleophile, that red star. This is my electrophile, that red dot. This is my good leaving group, that Br. So this is going to be an SN2 reaction where my nucleophile is the starred atom, my electrophile is the dot atom, my good leaving group is the bromine. We're going to do SN2 by doing a backside attack. Nucleophile, attack electrophile, kick out the leaving group, and connect the pieces. The reason why I star and dot my atoms is to keep track of all the atoms and not add too many carbons and not lose a carbon, right? So this is my starred atom here. This is the neo bond between the star and dot atom. This bond here is neo, which came from this pair of electrons. If I were to highlight that pair of electrons right there in yellow, that's this highlighted bond right there. The 2 electrons of this pair of electrons are these 2 electrons in that bond right there, that neo bond. Now we just attach the decorations, right? Br minus is no longer there. It went bye-bye. It's a Br minus floating around. And this dot atom here is attached to a CH2, CH3, which is this CH2, CH3 right there, right? SN2 reaction. Okay. Now, the second reaction that you need to know about this alkynyl anion chemistry is going to be with secondary haloalkanes. And this is going to be acting as a small, strong base now. Small, strong base. What about cases where you have a ketone? Yes, so you can have reactions with this with the ketone, right? And it can do that with the ketone. And you're going to see that towards the end of 118B. But for this midterm, Helix doesn't want you to worry about that yet. But you will need to worry about that for the final. That's good. So you went ahead a little bit. But this right here can attack ketones as well. Yeah. But for this midterm, just worry about these 3 reactions with the alkynyl anion for now. Okay. So if this is a small, strong base, and let's say this is hydrogen A and hydrogen B, which hydrogen would the small, strong base grab? The LAs were having fun torturing us with it in the problem set with the carbonyls, like the aldehyde and ketone reactions. Yeah. I heard those LA problems were more difficult than the Helix problems. So if you're able to do those, then you'll be like really ready for the midterm. But it goes overboard. Like if you like get overwhelmed, don't worry, because it's gonna be more difficult than Helix's exams. But if you're able to understand it, then that's good. Yeah. Yeah, functionally it acts similar to a Grignard, like MGBR or RLI. It's very similar. It adds carbon-carbon bonds. Yeah. Yeah. HB, it would go for HB because it is Zaitsev. So we're gonna have this base grab HB. The bond between HB and carbon is going to make a double bond over there, kick out the leaving group, and give us this alkene right here, and this terminal alkyne where the hydrogen that is attached to this carbon is this blue HB with the blue bond right there now. Or actually not the blue bond, because the blue bond went to make a double bond right there. So let's say if I highlighted this pair of electrons in yellow like that, this new bond right there that we made between that terminal alkyne carbon and HB is this yellow highlighted carbon bond right there, right? Carbon hydrogen bond right there. This blue bond I moved is now over here, right? If I highlight this bond in pink like that, that's this pink bond right there, right? So those are where the electrons are moving to. Yeah. Okay. So this is just the E2 Zaitsev, right? Create the Zaitsev alkene and a terminal alkyne. Now, the third reaction that Helix wants you to know with alkynyl anion chemistry for this midterm is epoxide ring opening. Now, let's say we have this epoxide right here. when you see a negative charge, right? No positive charge, no H2SO4. This is in basic conditions. Think of that as a base. And do you guys remember if we open up the epoxide in more or less subside in basic conditions? Less subside, right? So this would be my electrophile right here. The less subside of the epoxide. Attack that side, break open the ring that side, and then a lot of students get confused on how to attach those two pieces together. And this is what I like to do. I like to star my base or nucleophile. In this case, my electrophile, the dot right there. And for epoxides, I like to also dot the other carbon of the epoxide just to keep track of where things are, right? So let's draw in those pieces right now. Star, new bond between star and dot, right? That red dot right there is attached to this green dot right here. And that green dot right there is attached to an ethyl group like that, right? Now, we did not touch that green carbon at all. So we want to maintain the stereochemistry of that carbon. Do you guys remember how to assign RNS from 118A? This is also good for nomenclature. What would be the stereochemistry of this green carbon here? R or S? SR. So this is 1, this is 2, this is 3. Going this way is S, because the lowest priority group is on hydrogen, we keep it as S. It's going left because there is a tie between this carbon and this carbon. And if there's a tie, then we see what is attached to those carbons. This carbon right here is attached to, ignoring that carbon to the chiral center, 1 carbon and 2 hydrogens, right? There's 1 carbon and 2 hydrogens right here. Whereas this carbon here to the left is attached to 1 oxygen and 2 hydrogens, right? Hydrogens cancel out. Oxygen beats carbon in terms of atomic number. Yes, we would still count that oxygen right there because it is directly attached to that carbon that is tied to the other carbon, right? So this is S, and we want to maintain the S configuration of that chiral center right there. So this is more of a Levens thing, more than a Helix thing, but would this be a wedge or dash to make this S? Like, would this be wedge or would it be dash? Wedge. Right. Because oxygen here would be 1, this would be 2, this would be 3. That would go counterclockwise, stays as S. Yes. Okay, that's good. So when you see in synthesis, you have a terminal alkyne, and then you added a new carbon-carbon chain where there's an alcohol on the second carbon, right? Don't think of SN2. Like, because the reason why is because, let's say we have a terminal alkyne anion right here, and then you wanted to get to this point right here, right? And you try to do that by doing this reagent here. Let's say you make that the dot and you make this the star, right? This would not convert into that, right? The reason why is because this is a base or a nucleophile, right? It could be a nucleophile base depending on what the reagent is. We have an electrophile here. We have an acidic hydrogen here. In OChem, think of acid-base reactions as one of the fastest reactions you have. Acid-base reaction, very fast, right? So it's way faster than nucleophile electrophile reactions, like where the negative charge attacks the positive charge. Those are nucleophile electrophile reactions, which are slower than acid-base reactions. When you have an acid-base reaction competing with a nucleophile electrophile reaction, acid-base reaction would be way faster. So what would happen instead is that we're gonna just deprotonate that alcohol right there, right? So we don't want that, right? To actually get from here to here, you wanna put epoxide right there where the blue carbon is that less of carbon, and then acid work up as a result to protonate the O minus. Can you give an example where we attack the more subside? Yeah, so when we open up the more subside of the alkene, to do that, right, the three that will open up at the more subside are positively charged. So epoxides in acidic conditions will be protonated first, positive charge. Bromonium ion with the more subside, positive charge. Mercurium ion with a positive charge is going to attack at the more subside, because whenever you see a positive charge on a three-membered ring, right, think of that as the good leaving group, right? Good leaving group. And imagine it leaving, right? It could either leave here or here. Where would the positive charge be more stable at? The less subside or the more subside? Where would it be more stable at? More subside, correct. And that's why there's going to be a bigger positive charge on the more subside, residing in the more subside, because it's more stable there, more hyperconjugation there, right? So when you introduce some kind of nucleophile, it's attracted to the more subside, right? It's attracted to the more subside because there's a bigger positive charge there. And that's only when you have a positive charge on the three-membered ring, right? When you have a positive charge on the three-membered ring, that's when you know when to attack more subside. If it's neutral, like in the previous example, or when we opened up the epoxide right here, this epoxide here had no positive charge. It was neutral. That's why we attacked the less subside. Back to scenario number 2. Why won't the strong base attack the carbon bromine? Oh, this one right here. So the reason why it does not attack the carbon bromine is because there's a competing reaction, which is the acid-base reaction. When we attack that electrophile right there and kick out the bromine, that would be SN2, a nucleophile electrophile reaction, right? Where the nucleophile is this alkyl anion and the electrophile is this carbon here. But there is a faster reaction that happens before that, which is this acid-base reaction. We're going to deprotonate the alcohol instead, right? Which is going to give us this product here, the alkoxide ion with the O-, and a neutral terminal alkyne right there, right? Where this pink hydrogen here is that pink hydrogen right there. So this acid-base reaction happens faster than this SN2 reaction. Oh, for the previous one, number 2, right here, this one. Oh, why doesn't it attack the primary one right here? The reason why is because it competes. Like if you think about the SN2, E2, SN1, E1 table, let's say we have a secondary haloalkane right there, and we react it with Helix's favorite base, small base, ethoxide. What reaction would happen? SN2 or E2? E2, right? Because we have a strong base right here. Strong base reagent. So we would get that. But now, what if I told you we had this as a reagent? What would be the reaction? Yeah, it will be SN2 because Cn minus is a weak base, strong nucleophile. So we're just going to substitute that secondary haloalkane with Cn. SN1, I know, yeah, these are 119A reactions here, like N of 119A. SN1 would be if you have a weak base, weak nucleophile, and the ones that you're going to see is either water, H2O, or ROH, neutral H2O or ROH. Right, that would be SN1 reaction. Where the leaving group just leaves by itself, form a carbocation intermediate. Once you form that carbocation intermediate, you stop, watch out for any hydride or methyl shifts you could do, and then do that shift if necessary, and then attack with the weak base, weak nucleophile, and then deprotonate to get the neutral product. Can you explain why hydroversion is anti-mark? Yeah, I'll explain why hydroversion is anti-mark when I get to that problem in the predicted product. Okay, let's move on. Number 3. Okay, we can do this now. NaNH2. NH2 minus. What would that do to this terminal alkyne? Form the alkyl anion, deprotonate that alkyne hydrogen to create this anion, alkyl anion. Okay, now introduce it to this second reagent. What reaction would happen based on this reagent? It's one of the reactions that we just went over. Attach the chain, SN2, correct. So we're gonna do SN2 now, where this is my starred atom, this is my dot atom. And to connect them, we just connect the star and dot together. Right, star, dot, that's it, SN2. Okay, next one. So let's do the same thing. We deprotonate that alkynyl, that terminal alkyne to create this alkynyl anion. What will this alkynyl anion do with the secondary haloalkane here? Yeah, NaNH2 is the most common one. That's why I'm using it a lot. So when you say attached chain with one methyl coming off, are you saying that we're doing an SN2 reaction where this carbon here attacks this carbon and kicks out that leaving group right there? Okay, what kind of haloalkane is this? Secondary haloalkane. And when we went over the alkynyl anion reactions, right? When we have a secondary haloalkane, what kind of reaction do we do? SN2 or E2? E2, yes. So when you see an alkynyl anion, think of it as hydroxide ion or ethoxide ion, strong base, right? So if it's E2, we grab HA or HB. Yeah, so that's probably a tricky part right there when you have a secondary haloalkane. HB, right. Grab that HB, create the double bond there, kick out the leaving group. Those three arrows happen at the same time, simultaneously for the E2 mechanism, giving us our neutral terminal alkyne back and this Zaitsev alkene, right? This right here, even though it looks bulky, is still considered a small, strong base because the thing that approaches that HB is this part of the molecule right there, right? That part of the molecule is considered small because the rest of the part of the molecule just goes away in the void, like it just sticks out into the ether. Wait, so if we have secondary haloalkane, we attack the H on more sub side. Yes, we do Zaitsev E2. We attack the more sub alkene, the more sub beta hydrogen, right? So think of it as a small strong base, ethoxide or hydroxide. Yeah, which will do SN2 with primary haloalkane, but E2 with secondary haloalkane. So that's the biggest difference between them. Primary haloalkane would do SN2, secondary haloalkane would do E2, Zaitsev. E2 Zaitsev, more sub beta hydrogen. Any questions on this before we move on? Nope. Okay. Let's do number 5. Okay. So NaNH2 again, terminal alkyne again. Create that alkyne anion by deprotonating it. Now, what will happen next with the next reagent? Attack less sub to open up the epoxide like that. And this would do a backside attack, right? So usually we would invert this wedge into a dash, but we cannot make a dash here. The reason why is because of this sp hybridized carbon. Everything is flat and planar for that carbon. So if this is the star and this is the dot, that's a new bond midterm, it has to be flat and planar. And then if you want to keep track of this green carbon right there, that red dot carbon is attached to that green dot carbon, which is attached to a wedged O- and a CH2 isopropyl group like that. And the O- will just get protonated by H3O plus to become neutral OH like that. Yes. Okay. Any questions on this one? So this was epoxide ring opening in basic conditions. Would we? Yes. Well, since he gave you the epoxide here already, right? You cannot say racemic. Don't say racemic here. Wait, let me just put that note. No racemic. It has to stay as a wedge because nothing touched that carbon, so it stays untouched. You would put racemic if, like, in the mechanism somewhere, you had like a flat carbocation or radical, or a double bond making a ring, and then you could get either both wedge or dash everywhere. That's when you put racemic. But in this case, since it's already given to you, and that wedge bond there does not change at all, right? then we don't put plus or minus racemic. Yeah, let's do R minus RS for this one. So this one here will be 1, 2, 3, S. This one here will be 1, 2, 3, S. And it has to stay as S because nothing touched that green carbon. No inversion of stereochemistry, no randomization of stereochemistry. Yeah. Okay. Now, let's do the reduction reactions. Does anyone know what kind of reactions these are? Like what would these set of reagents convert this alkyne into? Hydrogenation. Yep, for the first one. And what's the cis one? What creates the cis alkene? What set of reagents? Lin-Lars, yes. And it kind of gets confusing on like how many carbons there are in the molecule. So what I like to do is I like to number like the molecule so I could keep track of, you know, where the atoms are. So let's say coming off of the ring. Let's actually number it the other way so then we can actually number it off of the ring. This is not nomenclature number, by the way. This is just like me numbering things so I could keep track of my atoms. Right, so coming off of the ring, there's 6 carbons coming out. 1, 2, 3, 4, 5, 6. Carbon 5, there's a methyl group like that. Okay. And for the sodium metal reduction, right? That's gonna, the dissolving metal reduction, that's gonna create a trans alkene between 3 and 4, where the alkyne was. 3 and 4, like that. Now, the cis alkene is the tricky one because you gotta draw it in a way where it's cis. So what I like to do is I like to draw out that cis configuration first, and I know that that's gonna be my 3 and 4. So this has to be 5, 6, methyl group at 5, 2, 1, and then the ring, like that. Right? So draw in what is important, and then draw in the decorations after that. Does H2 with PDC always hydrogenate all the way down to an alkane? Yes, it will always hydrogenate all the way down to an alkane. Right? We don't stop at the alkene. We go all the way down to an alkane with H2 PDC. Yeah, numbering them actually helps a lot because it keeps track of where the groups are, where the decorations are. So you don't put the double bond like right here or right here on accident. And that, like, the TAs would definitely check if you put on the right spot or not, like when they grade your exams. So numbering them would help you put them in the right spot. Does it matter if we flip it since there is no stereochem? No, it doesn't matter if you flip it. Like, you could have put the isopropyl up here, but that would put this rest of the molecule up here as well. So you could do that. It's still the same molecule. If only one equivalent of H2, then we could go down to allene, right? So if you get one equivalent of H2, it would like it doesn't really happen like that. Like it will happen in poor yield. Like if you have one equivalent of H2, like it will get in this poor yield. So we don't really do one equivalent of this. Like I haven't seen an example where you get one equivalent of that. I've seen examples where you go all the way down to alkane only. But if you want to stop at the alkene, then you got to use one of these reagents. Lin-Lars for cis alkene, sodium metal, and NH3 for the trans alkene, right? This sodium here is not positively charged. All the sodiums you see in like NaNH2, NaOH are positively charged, not this sodium here. This sodium has a radical in them, in the mechanism. Yeah, it will just make a small amount. Alkene will react faster than alkyne. So once it forms, it takes priority. Yeah, right. So keep that in mind for conceptual question, like why do we not get this in high yield if we react it with one equivalent of H2 PDC? The reason why is because once we form this alkene right here, then this alkene will be so reactive that it's gonna like react again somehow. Like even though we put one equivalent, but in lab, experimental, real life stuff, it doesn't stop here. We get poor yield of that. Right? It keeps going and until it gets to the alkane single bond. Yeah, put H2PDC. Like it's gonna be assumed that it's an excess for this one. Yeah. Don't put 2 equivalent. That's yeah. Don't put. Yeah, you can, but it's really written out as H2PDC to go down to the alkane. Okay, do you guys want to go over the mechanism of the dissolving metal reduction too with the radicals? Yes, okay, let's do that. So the name of this reaction is dissolving metal reduction. And there's 4 steps for this mechanism. And the first 2 are going to be repeating. The first step is going to be a radical addition. Second step is going to be acid base. And then we do it one more time. Repeat it. Third step, radical addition. Fourth step, acid base. Okay. So let's bring in a basic alkyne, a symmetrical internal alkyne, and have sodium radical come out floating nearby. Draw a single hook arrow to show the movement of 1 electron, attack one of the carbons of the alkyne, one of the pi bonds of the alkyne. Those 2 electrons are going to pop onto the other side of the alkyne. So that's probably the weirdest part of this mechanism, right? Where the sodium radical attacks 1 carbon of the alkyne, 1 electron, and that pops one of the bonds of the alkyne onto the other side, giving us this intermediate here. And we can actually get 2 intermediates, right? I'm going to draw it both, so let's number this so I don't mess up the things here. 1, 2, 3, 4, 5, 6. Trans alkene between 3 and 4. 1, 2, 3, 4, 5, 6. And I actually have this one as well. Right. When we write it down as just reaction for synthesis, do we just put the radical or just Na? You could just put Na, but it wouldn't be wrong if you put Na radical. Like you could just put it like this, but make sure to put ammonia liquid in there as well. Like ammonia liquid is very important. Like this reaction, you do need ammonia liquid, right? For the base NaNH2, you don't need ammonia liquid because that did not do anything in the mechanism at all. It's not involved in the mechanism. But this NH3 liquid is involved in the mechanism. So you do need to put this for synthesis if you want to make a trans alkene from an alkyne. Does the Na electron attack the less or more subside on the alkyne? Which side gets the 2 electrons and negative charge? So if you do have like a terminal alkyne right here, it doesn't matter. Like this radical can attack both sides. Right, it doesn't matter for this one. It does matter if you have if we did HBr, roar, and heat though. It doesn't matter where the radical attacks. But for the sodium one, it doesn't matter because you're gonna get to the same product either way. And I'm gonna actually segue to this mechanism after we do this mechanism because it's gonna be with radicals still. Okay. And I'm gonna show you guys the difference between this reaction and the next reaction here because like it's very weird on how he wants it as an answer. So we could either get this configuration here or this configuration here. Which one do you guys think is more stable? The trans configuration or the cis configuration? The trans configuration because the R groups are away from each other. Yes. The cis configuration here, there's steric hindrance going on. Ignore that intermediate. That's good. Yes. So now the next thing here is we're gonna use the NH3 solvent to protonate this negatively charged carbon and make it neutral, like this. Right? Now this carbon here is neutral because it grabbed that hydrogen from ammonia. Now, that was the second step, acid-base reaction. We do that again. Bring in another sodium radical, give this carbon another radical to make it into an anion, a negative charge, and then protonate that to get the final answer. Grab that hydrogen, kick out the NH2, and then give us our trans alkene, like that. So that's the mechanism for dissolving metal reduction. And you would get this trans alkene as the major product, high yield. Okay, now let me show you guys radical addition of HBr, roar, and heat to this terminal alkyne. Initiation. The roar splits into 2 OR radicals. Once we have the 2 OR radicals, we bring in the HBr to have one of the OR radicals interact with the H of the HBr and kick out one of the electrons of this bond between HBr onto the bromine, creating a bromine radical. So we're going to have a neutral alcohol and a bromine radical. That's the point of the initiation step. We want to get to that bromine radical right there. Yes, the lion. The lion sound. Okay. Now, once we have that bromine radical, then we move on to the propagation step where we bring in the terminal alkyne and the bromine radical. Now, this is where it matters, where we attack the more or less subside, like Sharon asked, right? Because we're going to form a positive charge here. Where do you guys think the positive charge is going to be more stable at? Would the positive charge be more stable at the Markovnikov side or anti-Markovnikov side? Markovnikov side, right? Since we want the positive charge at the Markovnikov side, we want that carbon to lose a bond. That means the anti-Mark side is the one that interacts with the bromine, right? Because when that happens, we're going to well, actually, it's not a carbocation intermediate; it's a radical intermediate. But it follows the same rule, same concept, right? The radical wants to be at the Markovnikov side, more substituted side, right? So we could get the radical there at the Morris subposition, and the Br is right here, right? And we could actually get it in the cis configuration right here. And Helix wants you to include like both products, trans and cis, for this reaction. But for this dissolving metal reduction, he only wants you to get the trans alkene. But for the radical addition of HBr, he wants both trans and cis products, right? What other step to quench that radical is to interact it with the HBr, right? Just give it a hydrogen and create another bromine radical. And then Br radical. So these are our two major products. If this showed up in predicted products, right? If you see a terminal alkyne reacting with HBr, ROR, and heat, draw both the trans and cis alkene. Termination, I don't know if he wants it in the mechanism, but it's just any combination of radicals to combine and end the radical chain, right? Any combination of two radicals. He said that in class, he wants trans for terminal and both products for internal. Oh, okay. He said that he'll give credit for trans and cis for terminal on PSO. Okay. He said trans for terminal. Okay, so let me erase this. So this is terminal. Major product would be trans. If you had an internal alkyne and you react it with ROR and heat, 1, 2, 3, 4, 5, 6, then you can get the E or the EZ alkene, or you can get the E alkene like that, and include both of these products as your final answer for predicted product if you have an internal alkyne. Okay, so that's the difference. Right. Terminal alkyne, trans alkene with the Br. Internal alkyne, get both the E and Z alkene. Okay, that's good. Thank you for letting me know. Okay. Okay. You wanted both are internal, not terminal. Terminal, trans major, internal, both trans and cis. Yes. Terminal, trans is major. And for internal, since there's 3 substituents, we can't say trans and cis. We have to say E or Z now. We'll get both E and Z products, right? Because the highest priority group for that carbon is that one. There's a same side for Z, E, opposite side, like that. Okay. That's good. Yeah. Thank you for catching that. Yeah, the same side. The same side. Okay. Different. Oh my god, I didn't see it like that. What the heck? It's spelled out like that too? Different. Okay, that's a good way to remember. Okay. That's good then. Okay. Now let's move on to hydrohalogenation of Okay, before we go over the future reactions, let me now differentiate between the 3 different types of alkynes I want you guys to know, because this will determine how many like different products you get. Terminal alkyne, symmetrical, and then there's internal alkyne. But there's 2 types of internal alkyne. There's a symmetrical internal alkyne, and there's an asymmetrical internal alkyne. Right? So a terminal alkyne would be if the alkyne was at the end. A symmetrical internal alkyne would be if the alkyne was in the inside of the molecule and the R groups are the same. And asymmetrical internal alkyne is if the alkyne is inside of the molecule, but the R groups are different. And this really does like matter because it tells you how many unique products you get, right? For these reactions. Okay. Now, let's do hydrohalogenation. Okay. Do you guys want me to like continue with the mechanisms here, or just predict the product? Or you guys want me to continue with like the whole step-by-step arrow pushing mechanism charges and everything with the mechanism? Go over spectroscopy. Max. Okay. Yes. Oh, yeah. Okay. Let's speed run this and then we can move on to spectroscopy and synthesis. Some of them in major for similar reactions. Okay, yeah. So this one here is gonna be very similar. HX and alkyne. We want to form the more stable carbocation, the more subside right here. If we want the positive charge there, that means the less subside is gonna grab the hydrogen, kick out the Cl, and convert that alkyne into an alkene where the positive charge is there, right? This hydrogen here is now here, but I'm going to leave that as invisible. Then a Cl minus comes in to attack that carbocation to give us this product here. And we don't stop at 1 equivalent here. That's going to be in poor yield. Poor yield at 1 equivalent. We're going to keep going because the alkene is more reactive. So we're going to bring in another HCl, attack that hydrogen, kick out the chlorine, form the more stable, more substituted carbocation. Cl minus comes in, attacks the carbocation, and gives us this geminal dihalide. Right? Geminal, meaning that the 2 halogens are on the same carbon. Right? That's excess. Okay. So that was the mechanism. I'm gonna show you guys how to predict the product quickly with a shortcut. Notice how the 2 halogens here attached to the more subcarbon, right? That's the most important thing about this pattern here, right? We're adding it to the Markovnikov side, Markovnikov carbon. Now, if we bring in this alkyne right here, what kind of alkyne do we have now? Symmetrical or asymmetrical internal alkyne? Symmetrical, right? Because the alkyne here is in the middle of the chain, and this R group here is the exact same R group as this R group right here. Right? It looks different because it's oriented differently, but methyl, ethyl, methyl, ethyl, same thing. So if we want to add 2 bromines on the more subside, it doesn't matter which one because each carbon is equally substituted, and you would get the same chemical environment if you add it to both carbons. So we only get one product here, where the 2 bromines are on one of the carbons of the alkyne like that. So for symmetrical internal alkyne, we only get one product like that. Okay. Now for number 9, it's a different story. Right? Because for number 9, we have an asymmetrical internal alkyne now, where we do have equally substituted carbons here. So we're going to get 2 different unique products. 2 chlorines for each carbon of the alkyne. One there. And another one here. And this is where number could be useful to keep track of your carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Where the alkyne was between 2 and 3. So our 2 chlorines could have been on carbons 2 or carbons 3, like that. Yeah. For 8, we don't put racemic because there's no chiral center. Well, there is a chiral center here, but they didn't give wedge or dashes. But the one that we like formed, this is not a chiral center here, so we don't put wedges or dashes there. Yeah, we only put like wedge or dashes on chiral centers that we form, and if it can change and all the chiral centers can change in the molecule, that's when you put racemic plus or minus. But if there's a pre-existing chiral center somewhere else in the molecule that does not change at all, you cannot say racemic because there will be diastereomers, and then you would have to like draw out that diastereomer or say like 4 stereoisomers or 6 stereoisomers, how many stereoisomers there are. Right. Okay. Okay. Number 10. So for this one right here, this is halogenation of an alkyne. Let's do the same mechanism as the alkene. LIBR here is just a catalyst. Ignore that. What is the intermediate again for this reaction that gets formed? Three-membered ring, polonium ion, bromonium ion, or chloronium ion. Yes, with a positive charge. And we have a protic solvent here, CCl4, so there's no competition of nucleophiles, no water to attack, no alcohol to attack. We have just a Br minus to attack, right? And it doesn't matter which side we attack because it's going to give us the same product anyway. It would matter if we had water though, which we're going to go over after this. And this is going to be anti-addition, so make sure your 2 bromines are trans to each other, anti to each other like that. And you can stop here. You can stop here. If you see on the reaction, there is one EQ, one equivalent of Br2. This is your final answer. Don't keep going, right? Because you can actually isolate this in high yield for halogenation of alkyne, right? You cannot do HBr in 1 EQ, right? Like it's going to keep going all the way until you get a geminal dihalide. But when you get an X2, you can actually stop at this product here with 1 equivalent. Yes, we'll do one with H2O present after this one. But if you do have excess, then we just do the same thing. So a lot of these alkyne reactions are very similar to, you know, the alkene reactions times 2 because of the extra pi bond. And there's some extra stuff like Lindlar's catalyst and keto-enol tautomerization, which we're going to go over now before we move on to the one with the H2O. Okay, so if you have excess Br2, we just like over-brominate both carbons of the alkyne, like bromines everywhere. It's went crazy. Would the reaction proceed if it was just Br2 without the LIBR? Yes, the reaction will be uploaded tonight as soon as possible. I'll send it to the Discord and the school website with the notes as well. And I heard you guys like in the tomorrow section have it at 1 p.m. or something like that. So hopefully you guys can review it in the morning before then too. So LIBR4 just increases the reaction rate. I think it can still happen without LIBR, right? But on all the alkyne reactions with halogenation, I've seen it with LIBR, but it can still happen with LIBR. It just speeds up the reaction with it. So I'm saying that if it was 1 EQ-Br2, we stop at the alkene. But if you had excess, we keep going to from the alkane. Yes. If you had 1 EQ of Br2, you stop here at the alkene with the vicinal dihalide. But if you had excess, then you stop at the alkane with the vicinal tetrahalide. Yeah. Okay. So, oh wait, I forgot to do this one. So I'm gonna have you guys do this one. What do you guys think the product is gonna be for this one here? If we have an asymmetrical internal alkyne reacting with excess HCl, how many products would we get, and what would it look like for this one? Two different products, right? And what would the products look like? Would it be a vicinal dihalide or would it be a geminal dihalide? Geminal dihalide, right? Oh, so be careful, Khadija. This alkyne here, we won't put a lot of chlorines like that. That's when you have excess Cl2, like this, right? This is HCl, so be sure to know the difference between HCl versus HCl. Yeah, right. That's very important, especially for the conjugated addition with thermodynamic versus kinetic product. Oh my gosh, there's so much going on in that one. But okay, let's keep going. Let's do this here. Cl. Cl. Yeah, these are your two unique products here, where we put two chlorines on each carbon of the alkyne, just like that. You can number it if it helps you keep track of atoms. 1, 2, 3, 4, 5 coming off of the benzene. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Where the alkyne carbons were 2 and 3. So that's where you put the chlorines. 2 chlorines on carbon 2 for one product. 2 chlorines on carbon 3 for another product. So that's how you can keep track of the right carbon. Okay. Now for this one we did 10 already. Yep. Okay. Now 11. For this one, with 1 EQ of CO2, what would the product look like? And what would be the stereochemistry be like as well? Cl trans to each other. Yes. Vicinal dihalide. And do we have an alkane in the product or an alkene in the product? Alkene with Cl trans to each other. Yes. No wedge, no dash. Why don't we have wedge or dash here? Flat. Yes, flat. Flat and flat. It's good. And this is anti-addition, so make sure they're anti to each other, like that. Nice. Okay. Before we move on to the next one with water, let me go over eno and tautomerization with you guys in acidic versus basic conditions, because you do need to know that for the mechanism as well. Okay. So an eno is when you have an alkene next to an alcohol, right? Alkene next to an alcohol. Alkene, alcohol. Eno. So let me just draw you out different enos so you get used to seeing them. Right, so all of these here are enos. Whenever you have an alcohol right next to an alkene, then that's an eno, right? And they don't stop there. Like, think of these as the intermediates. They would spontaneously, naturally convert into a carbonyl. Right, where the carbon that held the alcohol, let's color code that in pink. Like all these pink carbons here holding the alcohol is now the carbonyl carbon, right? We got rid of the alkene, right? We got rid of that carbon double bond carbon. We got rid of the hydrogens of the alcohol, and we put a double bond between the carbon, pink carbon, and oxygen, right? And that's tautomerization. Taut, yes. And you do need to know the mechanism in acidic conditions versus basic conditions. Okay, let's look at it in acidic conditions. And I'm going to ask you guys a series of questions here. don't worry if you guys get it wrong, right? Because this is gonna like break some previous stuff that you guys thought about before about the pattern recognition, right? But I'm gonna explain why conceptually so you guys can understand why this is the case instead. So if we have this enol here and we have H2SO4 floating around, well, some of you guys may already know this, but what's gonna get protonated here? What atom is gonna get protonated from the enol? Yes, the alkene. Right, the pi bond gets protonated, not the oxygen of the alcohol, because previously when you saw that alcohol without the alkene there, that would usually get protonated. But in this case, the alkene is going to get protonated. But which carbon of the alkene? Carbon A or carbon B of the alkene? Carbon B, right. And the reason why, conceptually, that you can think about it is like this. We see that we can do resonance by pushing this pair of electrons down to make a double bond there, which pushes that double bond onto that carbon, giving that carbon a negative charge. And when I draw out the resonance structure here, we see that there is a full-on negative charge on that carbon right there, right? Where if we say that that's the carbonyl carbon, and this is the alpha carbon, this alpha carbon here of the alkene has a full negative charge, which is why it's going to be the nucleophile or base, depending on what reagent we give it, right? And because we're given acid here, this starred carbon here of the alkene is going to be the base. So we can form a carbocation, right? By like just directly attacking the hydrogen like that, kicking out an HSO4 minus to get this cation right here, right? But that can be resonance stabilized by this alcohol hydrogen right here, which is going to create this carbonyl with a positive charge on oxygen. And then from here, you could just deprotonate that positive charge oxygen with the HSO4 minus that we formed earlier to get the neutral carbonyl, right? But a quicker way to get to this point here is to form a carbon double bond oxygen, right? Bond right there. And we know that that's going to break the octet rule. So we know that there's going to be a negative charge here, which is going to attack that hydrogen and go directly to that point right away for the mechanism. So you can do it both ways, right? In mechanism, if you protonate the alkene right away without pushing the double bond down to make a carbonyl and you get the carbocation, make sure to draw the resonance structure at the end to get the right structure, right mechanism. But if you want to skip this carbocation here and go directly to this carbonyl with a positive charge, you could push this pair of electrons down to make a double bond there between the carbon and oxygen, which would have this alkene attack the hydrogen, kick out the HSO4 minus, and get to this intermediate here. Right, which is then going to get deprotonated to get the final product. So both ways would work. Both routes would work. Any questions on that mechanism, acidic conditions mechanism? Okay, now let's move on to basic conditions mechanism. If I have this enol here, and I'm going to draw it out explicitly like this, and I have some kind of base floating around, like hydroxide ion, what's going to happen between this enol and hydroxide ion? Deprotonate the alcohol, give the oxygen a negative charge, right? And once we have the negative charge here, here's the important part. You're going to see a lot of these reactions at the end of 118A because there's going to be a truckload of reactions that hit you at the last week or the last 2 weeks. And it's all about this guy right here, this alien-looking enolate ion, right? And its cousins and its family members. So let me show you the resonance structure of this before we move on. We could push one of the pairs of electrons down to make a double bond there and create the carbonyl, and push that double bond over to create a negative charge on that carbon right there. Right? We maintain the negative charge overall, right? Negative charge here and negative charge here. Yes. Or midterm 3, not so much, because midterm 3 is going to be about benzene chemistry and Diels order. There's no enolate chemistry as much for midterm 3, but the final for sure. So after midterm 3, post midterm 3, final material will be a lot of these reactions: enolate, enamine, enol, and their family members, right? In acidic conditions, basic conditions, forward mechanism, reverse mechanism. So I would recommend you guys to, like, if you guys have time, finish midterm 3 material early, so you guys can get started on final material early, which I will go over in my office hours if you guys like can have time to, like, show up. Or I'll have recordings of it uploaded to YouTube anyway, so you guys can just watch that as well. Because I will be going over as early as possible for the final material, because I don't want you guys to get overwhelmed, because that's like the end of 118A. Like, you guys notice how at the end of 118A they threw in the alcohol reactions at you, ether reactions at you, SN2, SN1, E1, E2 reactions at you. There's a lot of reactions at you at the last 2 weeks. It's kind of like that, like the end of 118A. Yeah, the end of 118B is like very bad. Like, that's when people get overwhelmed the most. That's when I like started started panic in OChem. Yeah. Does alkene grab H2O while at the same time oxygen forms a carbonyl? Yes, it will be, Khadija. Yes. Yeah, you got it. So given these two resonance structures here, which one would be major and which one would be minor? Yeah, organic chemistry tutor is very good. And also I also watched this website here. He also helped me understand things very conceptually. Like, I got a lot of things from this guy here. Yeah, organic chemistry tutor is good. Chad's prep is good. Joe Chem's good. Yeah, the people in the Discord is good too. The tutors are there. Yeah, ACC tutors. Yeah. Okay, so given these resonance structures here, which one would you guys say is the major resonance contributor, and which one would you guys say is the minor resonance contributor? Major on the left. Yes. Like, which one is the major resonance contributor? Which one is minor? This one is major. This one is minor. So 118A stuff, right? Because the negative charge here, whoa. Do you guys remember the very first thing, the number one rule for resonance structures? Like, what's the most important factor? Octet rule, yes. So even though like the negative charge is on the less electronegative atom, if that has the all that octet rule, then that's the major one. But every atom here has the octet rule, and every atom here has the octet rule, so we don't have to worry about that. Then we worry about the charge and where it's stable at. We have a negative charge here and a negative charge here. We see that it's more stable at this more electronegative oxygen atom, so that's why this is the major one, aka the more stable one, aka the unreactive one, less reactive one. This is the unstable one, the more reactive one, right? Which is why this alpha carbon here is the nucleophile, right? So when we bring in water, again, the O minus does not get protonated, right? Because if it did, it would go back to what it was before, and that's an unproductive step. So we would have to form a carbonyl, right, by using one of the pairs of electrons on oxygen, and have that alpha carbon attack a hydrogen, kick out an OH, and give us our carbonyl with a base catalyst being reformed. I thought carbonyl was more stable than alkene. Yeah, so carbonyl is more stable than alkene, right? Which is why we're going towards that carbonyl bond, carbon double bond oxygen, and protonating this negatively charged alpha carbon to get this more stable carbon double bond oxygen. You are right. Yeah. Right. Oh, so the major and minor resonance structure here is talking about more in terms of where the negative charge is at, like the negative charge on the oxygen versus the negative charge on the carbon, alpha carbon. But this carbon double bond oxygen here is more stable than this carbon double bond carbon right there. Yeah. And that explains why like this alpha carbon here is more reactive than this O minus right here, right? Because it's less stable. It's unstable, very reactive, which is why we use that to attack a proton instead of the O minus. Yeah. So they're both pretty quick mechanisms in acidic and basic conditions, but this is included at the end of like reaction mechanisms like hydration, hydroburst, and oxidation, and the next one what we're about to do, X2 with water. Okay. Any questions on this before we move on to that? in acidic or basic conditions. And the way that you tell which conditions you're on is to look at the reagents. If you're given H2SO4, you're in acidic conditions. If you're given NaOH, you're in basic conditions. Now, if you're given water, right, it's like basically amphoteric, both acidic and basic, but in the mechanisms I've seen so far, water is used as an acid, most likely. Okay, let's move on to 12. Okay, so let's do 1Q of Br2, form that bromonium ion. And now we have a Br minus floating around and a water floating around. Which one would be my nucleophile? H2O, yes. Because there's a million times more water than this one teeny tiny one equivalent of Br minus that we kicked out in this first step. Right, that H2O is our solvent. There's a million of them, which would overpower this Br minus. Now, if that's the solvent right here, which side would we attack? The more subside or the less subside? What kind of conditions are we in here? Markov-Nakov side, right? Because notice how at the very beginning of the session, someone asked like, how do you know if you attack the more subside or less subside? Or can you do an example of attacking the more subside? We have a positive charge here, right? On the 3-membered ring, which is a good leaving group, which makes the bigger positive charge on the more subside like that, which is why we attack the more subside instead of the less subside. Pop that open and give us this intermediate here. And since this is like anti-addition, I'm going to make them anti. Okay. Now, what can we do to neutralize that? Positively charged oxygen. Water. Yes. Is it true that in basic conditions you attack the less subside? Yes. In basic conditions you attack the less subside. And you know that you're in basic conditions if your 3-membered ring has no positive charge. If it's neutral, then you're in basic conditions, which would attack the less subside instead. Okay. And we could use water to attack that hydrogen. Have that OH there. Benzene here. Okay. Now, do we stop here or no? What do you guys recognize here? What functional group do you guys recognize here? We do tautomerization. Yes, we have an enol right here. That very special guy right here. Enol. We don't stop there. We keep going. And since we have water here, we're going to do it in acidic conditions because we started off with acidic conditions. And to maintain the consistency of the reaction, we're going to do this in acidic conditions. Yes. Top time. Okay. So form carbonyl. Get protonated with the water. And Br. OH plus. And then hydroxide ion that gets formed. Comes back, grabs the hydrogen. And gets our final product here. Right. And now we see that we have alpha bromo carbonyl. That's very important to know. Make sure to know this relationship because you can see this in synthesis. If you see a carbonyl or a carbon double bond oxygen, right, next to a bromine, right, where the bromine is on the alpha carbon of the carbonyl, then you know that we did 1-EQBr2, LIBR, and water, halogenation and water, right? Because we know that this carbonyl here was an alcohol before, right? Because that water gave it the alcohol, but we didn't stop there because we tautomerized this enol into the carbonyl, like that. Yeah, this is a different way of drawing the benzene. Like instead of drawing out the resonance structures of like these right here, like the double bonds right here, we know that the double bonds can be alternating, which is why I drew that circle, which is a faster way of drawing that benzene ring. Yeah. Yeah, it's just a faster way. I got tired of drawing like these bonds. Yeah. The circle here is showing the electrons circulating around the benzene ring, delocalized around the benzene ring, doing resonance around the benzene ring in the pi system. Yeah. Right. When do we know when to form the ring intermediate with Br, and when do we not? Does it only form Br2 with one equivalent, or does it also form an excess? So yeah, we always form the polonium ion ring, the 3-membered ring, with any x2, right? If it's 1 EQ, then we do it one time. If it's excess, then we do it how many times we can with all the pi bonds, like double bond, triple bonds. Right? If we do triple bond, we could do it 2 times, right? One time, stop at the alkene. If you have another equivalent, do it another time to go to the alkane. Yeah. How do we know when the charge on bromine is positive? So the charge on bromine is positive when the halogen bromine has 2 bonds attached to it, right? Because bromine with 2 bonds and 2 pairs of electrons has 1, 2, 3, 4, 5, 6 electrons to itself. But on the periodic table, it wants 7 electrons to itself. It's on the 7th group. 7 minus 6, positive 1 for more charge, like that. Right? Because usually halogens want 1 bond, right, to be neutral. Like bromine, chlorine, iodine, fluorine, they want 1 bond to be neutral. When any halogen has 2 bonds, then it's going to be positively charged, like that 3-membered ring. Yeah, of course. Okay. Now, this was the easy case because of the terminal alkyne. It would be different if we have internal alkyne. Yeah. Let me go over spec at 10:30 because spec is going to require some time to explain. So let's pick and choose 2 more reactions to go over here. Do you guys want to go over well, let's see here. Do you guys want to extend this to 3-hour session or nah? That's too long. Because I just realized there's so much information. There's so much. Okay. 24, 26. Okay. Oh, polyene. That's the one with the. Okay. Yeah, polyene, is that included in the next midterm? The polyene? I thought that was in the midterm 3, the polyene reaction. NBS. It is. Okay. Let's do NBS then. Yeah, there's a lot of NBS questions. Let's do this one. So let me give you a simple alkene like this and react this with NBS and light. When you see this reaction, think of allylic bromination. Right? So let me give you guys what that means. These carbons here on the alkene directly is called the vinylic carbon. Right? That's a position term. The carbon right next to it is called the allylic carbon. You could also call that the alpha carbon if you want, right? Because that's the first carbon away from the alkene. But in this case, we're going to think about the allylic carbon. And this term here is very important, especially for the thermodynamic and kinetic product. Now, before you predict the product, think of this as an intermediate. There's going to be a radical right there, intermediate, which can do resonance with this double bond with those arrows. All these single hook arrows show the movement of 1 electron. This 1 electron here is going to make a double bond here with that 1 electron right there to make a double bond right there. That means the other electron here is going to make a radical on the other carbon, giving us this resonance structure here. Right? And then once you have that, wherever your radical is, just attach the bromine right there to get your final product. Right, and these are your 2 final products here for NBS. So that's the quick way to predict the product. The mechanism is going to be initiation, propagation, termination. And once you get to the radical, then you do this here. Right. Now, there is a more tricky case where, let's say you have 2 allylic positions, right? We have 1 allylic position here, another allylic position here. Yes. Include both NBS products on the exam, right? With coming from both radical intermediates, from both resonance structures. Okay. Now, if in this reaction here, I gave you guys only one allylic position to worry about, which give us only one resonance set. Now, in this case right here, let's say this is carbon A, carbon B. Where would the radical be more stable at? A or B? A, yes. Okay. Let's put that radical right there and ignore the radical on the other allylic position. Then let's do the resonance arrows to get to the resonance set. Like that, right? And then those two intermediates will lead us to our two final products right here. Just like that. Include both products, right? This one was a little bit more difficult because you had to choose between this allylic position versus this allylic position. Okay. Now I'm gonna have you guys try 21 and 22, and then when you guys finish, send me through the Zoom or type in the chat on what the products would look like. Where do the initial radicals come from? Yeah, so the initial radicals, you would have to know the mechanism for that. NBS is a structure, but on the study list, he said like you don't need to know the mechanism from NBS, right? He said you need to know the mechanism from BR2, right? I think for the mechanism for this reaction. Yeah, that's correct. Okay, so here's like the mechanism. It will have initiation, propagation, termination. Initiation. If you do BR2, then you could split out those BR2 into these two BR radicals right here. Propagation. Let's bring in a simple alkene like this. And let's say we create a radical right there, like this, right? And once we have this, then we could form the resonance set that leads us to our two different products, right? And then our other bromine radical will then just interact with that radical to give us our final products, right? And I'll explain the arrows here. The arrows for radicals are always so weird because like there's like single hook arrows and there's like split in half and everything. It's always so weird. Right, so the first initiation step here was that the BR2 right here, those two electrons, one electron went on one bromine, the other electron went to the other bromine, creating two bromine radicals. Once we have these two bromine radicals, then I moved on to propagation where I brought in the alkene. And there might be a conceptual question here, right? There's a multiple choice question where which hydrogen, A or B, would be easily broken in the NBS reaction, A or B, right? And that's why you have to see which radical is more stable at position A or position B. It would be at position A because it's allylic, yes. So that's why this BR radical here is gonna bond with this H to form HBr. Include that if this is in the mechanism, side product. And then this bond here, the other electron goes to that one carbon right there at the allylic position. And then we do resonance with that allylic radical like we did previously. And then to attach the bromines to those radicals, we just do these two arrows here like that. Right, and let me color code these arrows in red. Like this. To give us our final products like that. Any questions on this mechanism? Yeah, both of them would be products. Yeah. Okay. Does anyone have the answers for these ones? 21, 22? Oh, I see what you did. So Sharon, you put the bromine on this carbon and this carbon. What position are these carbons here? Vanillic, or allylic? That's good because like we're making these mistakes now, so then we avoid them on the exam, you know. So like what are these positions called? The ones directly on the alkene, vanillic or allylic? So the allylic carbon is gonna be one carbon away from the alkene, like that. These carbons that are directly on the alkene is vanillic, right? The ones directly on the alkene is vanillic. Yes, right. So it's vanillic. And in this mechanism, right, somewhere in the intermediate, you're going to have a radical at the allylic position right there, right? Because that's the only allylic position we have, the only one we have to worry about. So we're going to put allylic radical right there. And we could draw out its resonance structure with those arrows like this. And that would give us these two intermediates, which would lead us to these two different products here. Br there at that allylic carbon, and in the other resonance structure, the alkene shifts here, putting the Br at that allylic carbon right there. Does that make sense? Any questions on this one? Yeah. Where the Br radical attacks like these ones here to get to the final product. Oh, okay, yeah. But wouldn't the alkene be less stable at the end? Yes, so the alkene is less stable here at the end. So this is gonna move on to kinetic and thermodynamic product. Kinetic product will come from the most stable intermediate, either cation or radical. Thermodynamic product will make the more stable product, right? In this case, alkene in these reactions. So we have a tertiary allylic radical here. We have a primary allylic radical here. Now, if we talk about the alkenes, this is a mono substituted alkene. This is a tri substituted alkene. If we're looking for the kinetic product, we look for the more stable intermediate, which is this tertiary allylic radical here. So this would be our kinetic product. And if we're looking for the thermodynamic product, we're looking for the more stable alkene, which is this tri-substituted alkene. This is our thermodynamic product. But for NBS and light, Helix would not give you temperature, so he would expect you to do both kinetic and thermodynamic product. All right. The less stable alkene would be the kinetic product that came from the more stable carbocation, and the more stable alkene will be the thermodynamic product. Like that. Oh, how did we get the radicals at the allylic position right here? Like at this position? Yes, okay. So the initiation step from Br2, this is the bond between Br and Br. Those two electrons right there will homolytically cleave. So one electron of that bond is going to go to that one bromine. The other electron of that bond is going to go to the other bromine, giving us two bromine radicals. Once we have the two bromine radicals, we move on to propagation, where we then bring in the alkene right here. Then we look at which position it's going to hold the radical the best, have the best stability for the radical, which is this allylic position here because it could do resonance, right? And resonance would make things more stable. So to do that, this Br radical that we formed at the initiation step right here is going to, so this is an invisible hydrogen right here that I drew out. It's going to bond with this invisible hydrogen, right? That bond there between the carbon and hydrogen has two electrons. One electron is going to bond with the Br radical. The other electron is going to create that radical right there at the allylic position, which then like creates this radical at the allylic position, and then we can do resonance. And then once we have that, the Br radical, another Br radical, can just attack that allylic radical to get the final products. Yeah. Yeah. There's H's there, invisible H's. Like this goes back to like I think he revealed it with the 118A reaction too, right? Like free radical halogenation reaction with the initiation, propagation, termination. This is coming back for that that stuff. So basically, we have our bromine go to the hydrogen that is one bond away from the alkene. Yes, one bond away from the alkene. The bromine will go there as one of the products, right? But that's not the only product because we could do resonance and get the other product here. So don't automatically think we put a bromine right here. First, think you add a radical there, right there first. Radical at the carbon next to the alkene, right? The most stable carbon next to the alkene. And then when you do resonance and you get your two radicals, then you just attach the bromine to those radicals right there to get your final products, right? But you're right, one of the bromines would be attached to one of the carbons next to the alkene, but that's not the only product that we can get. Radical will always form on allylic. Then we do resonance to, yeah. So the main point here is this radical at the allylic position right here, right? That's the main point. We want that for NVS, when you see this reaction, always think of a allylic radical. And once you do that allylic radical, then you do resonance to get both products that he wants. Great. Any questions on this? And Sharon, you got the right answer for 22, right? You had that radical at the more stable position, the tertiary position, you put a bromine there, and then you did the resonance to get the radical at the other position, and you put the bromine there. So 22 is correct. And that was the harder one, right? Because there were like two different radical positions, and then you put on the right one. Two possible allylic positions, right? So for 22 right here, this is our alkene right here. These are the vinylic carbons. These are the allylic carbons, the pink ones, right? Then in the intermediate, we know that we want to form an allylic radical intermediate. But there's two allylic positions, here and here. The top one is more stable, so I'm going to put the radical at the more stable position right there, right? And now I could do resonance and get the other resonance structure like that, right? Where I have a radical here, alkene here. And to get the final products, I just attach the bromine to wherever the radical was, wherever that carbon radical was. Like this. And like that as well. Yeah. Yes, H2. Well, it's not BR2 with ROR, it's going to be HBr and ROR, right? HBr and ROR would attach to the vinylic position. And we don't say vinylic radical because, oh yeah, actually, yeah. The radical would be at the more sub position. But BR doesn't attach to that position. BR attaches to the anti-mark side. But there is a radical intermediate in that mechanism as well, at the mark side. Yeah. There is no wedge and dash. So there actually is wedge and dash because there are chiral centers being formed here, right? So like you can have wedge, dash, plus minus, or you can have wedge, plus minus, because that is a chiral center right there. And we can get chiral centers because this is a radical, flat and planar. So when it attacks the bromine, it can attack on the top or bottom side. Yeah, so for Helix, he would want these stereo centers as well. Doesn't the second product require going through the less stable radical first? Yes, the second one goes through the less stable radical, right? But it makes the more stable alkene, which is going to be the thermodynamic product. Whereas this one here makes the less stable alkene, but comes from the more stable radical, which is the kinetic product. So that's the differences between this product and this product. One is kinetic and one is thermodynamic. You're going to get this more if you have high temp. You're going to get this more when you have low temp, right? So the second one here goes through a less stable radical, but eventually forms the more stable product, alkene. But we don't really talk about kinetic thermodynamic in NBS. We talk about that more in conjugated dienes with addition of HX and addition of BR2, addition of X2. The resonance, yes. Let me draw this resonance out. Look right here, right? I first put the radical on the more stable position here, and then to do the resonance, I made a double bond here by moving that one electron over, and this bond right here has two electrons. One electron is going to go to bond with that one electron to make a double bond right there. There's one more electron in that bond, which goes to the other carbon right there, creating that radical right there, right? Because there's two electrons in this bond right here, and those two electrons came from those two electrons right there. And this one electron is that one electron right there. So resonance for radicals is very weird because of these single hook arrows. Do we have to include stereochemistry on the exam? Yes, you do. For predicted product, make sure to put stereochemistry like plus minus or for isomers or something like that if there's a chiral center. Why won't the H opposite to the methyl be removed? H opposite to the methyl. Oh, this H right here. So this H is removed because somewhere in the propagation step, right? If I draw that H out next to the methyl, and we have a bromine radical that got formed in the initiation step, forms an HBr with that bromine radical, and that bond right there, one of the other electron is going to create a radical right there, giving us this radical right here. So there's no H here because the H was interacting with the Br, forming HBr. So that's the propagation step of the mechanism. Why won't the H? Is this symmetric? So that's why there's only two products. This is not symmetric, and there's only two products because. Well, let me give you guys a step-by-step process on NBS reactions, right? So what I think about is NBS. So NBS new. First, well, when you guys want to think about it and to predict the product quickly without the mechanism, put radical on most stable, aka substituted allylic carbon. Then draw resonance structure of that radical. Then the last one is to attach bromines to those radicals. Attach NBS bromine to those radicals. So those are the three steps that come to my mind when I want to predict the product quickly with NBS and light. What tells you that there's BR and that is assumed or given with NBS? So the mechanism will have something to do with NBS structure, which is like a ring like that, but you don't have to worry about that for this test. You just have to worry about the BR, right? And that's what Helix said on his study list. So don't worry about the NBS part of the mechanism. Yeah. The other pink dot. Oh, this one right here. Like, why don't we put a radical right there? The reason why is because this position is more stable for the radical, which is why this hydrogen here stays there because it's not going to interact with the bromine radical. The bromine radical would prefer to interact with this hydrogen to form the more stable radical intermediate here. Right, so that's part of this step right here. Put radical on the most stable, most substituted allylic carbon, right? We have two allylic carbons here, the more sub-allylic carbon and the less sub-allylic carbon. We want to put the allylic carbon at the more sub position instead of the less sub position. So we ignore that one. Even though that is a allylic carbon, we don't interact with it because there is a more stable one here. More stable, more substituted allylic carbon here, right? So here's the step-by-step process on what I think about when I predict the product with NBS and light. Okay. Okay, you guys want to go over spectroscopy? I got a lot of questions on those earlier. Let's do it. Which exam do you guys want to go over? I have both sections of 23 and both sections of 24. Okay, I will share. Yes, the octopus. The octopus one. Let me download it and send it to the Zoom chat here. The 1 to 23 ones. You guys have access to the 24 ones already, right? From Canvas? Yes, okay. Let me send you guys the 23 ones. I got scared setting up the Discord because I saw like it's not allowed to send the whole exam. So I'll just send it here. Let's see. Okay. Exam 2, winter 23A blank. Winter 23, midterm 2A key. Winter 23, midterm 2B blank. Winter 23, midterm 2B key. Okay. Get it. I used to have a Canvas course when I was the AETC content review leader for 118A, like when I had like post all my notes, review sessions there. But I get his resources from some people. So here's the everyone in meeting. 2A key. 2B blank. And 2B key. Okay, blank key, send. Okay. Yeah, mass spec is going to be multiple choice with the alkyne paprogelic fragment, right? So it's going to ask you like which is the major structure. So like that, right? Like A, B, C, or D for mass spec. Okay, and the answer would be C because it is on a paprogelic position, which can do resonance with alkyne. Okay. Okay. Let's go over spectroscopy first, and then I'll do that after. Yes, I'll review that after. So which one was the octopus one again? 24 or 24? 24A or B? 24A. Okay, yeah, I'll show that. 24A. Yeah, so this is the paprogelic one. Actually, this is a pretty quick thing to go over. Let me just draw on one big molecule for you and show you what this means. We said earlier the alkene carbons are the vinylic carbons directly on the alkene. One carbon away from the alkene is the allylic carbon. One carbon away from the alkyne, paprogelic carbon. Right, so allylic, vinylic, paprogelic. Yeah. Huh? Yeah, like Justin said, it's like allylic, but next to a triple bond, next to an alkyne. Okay. Spectroscopy. Octopus. Okay, so for this one here, we have signals 4 to 6, and I want to show you guys what I think about when I think about HNMR. So there's different regions that represent, you could say, like functional groups, but not really, like de-shielded regions versus shielded regions between 0 to 12. The more de-shielded the region is to the left side, the more easy it is to distinguish where the hydrogen is. The more shielded the hydrogen is, the harder it is to distinguish what hydrogen is, because there's so many like things going on here. It's over here, it's more crowded, right? Over here, there's less stuff going on, so it's more easy to tell where the hydrogen is at. 0 to 2 is the boring alkane sp3 carbon hydrogen bond, right? Where the hydrogen is not near any electronegative atom, not near any pi bond, not near any double bond, carbonyl, right? Just next to single bonds, that's it. Between 2 to 3, that's what I call the alpha region, right? This is the region that is very sneaky, because those hydrogens there are going to be on the alpha carbon of some pi bond, or it could even be a terminal alkyne hydrogen. That's the weird one. So all of these carbons here in red are alpha carbons. They're one carbon away from a pi bond, a double bond like alkene or carbonyl or triple bond. All these alpha carbons here, where the hydrogen is at, is going to be between 2 and 3. It could even be a terminal alkyne hydrogen, right? This is not an alpha carbon here, but that terminal alkyne hydrogen is going to show up between 2 to 3, like that. Now 4 or 5, I would say, like let's say 3 to 5, right? 3 to 5 is the electronegative region, where the hydrogen is attached to a carbon that is attached to a electronegative atom: oxygen, nitrogen, chlorine, bromine, iodine. When hydrogen is next to some electronegative atom, between 3 and 5, right? Now between 4 and 6, right? Four and 6, that's the alkene hydrogen. So the hydrogens directly on the alkene is going to be between 4 to 6. 6 to 9, that's when you think about midterm 3 stuff, benzene hydrogens, right? And in my opinion, benzene chemistry is like much easier than alkene and alkyne. Chemistry is much more pattern recognizable, much more easy to pick up on. So midterm 3 is probably going to be easier than midterm 2. Midterm 2 is going to be probably the hardest, in my opinion, like harder than midterm 1 and 3. 10 is going to be the aldehyde hydrogen, right? And 12 is going to be the carboxylic acid hydrogen. So this is what I think about when I think about HNMR. Now, between 4 to 6, this alkene region right here, there's complex splitting. We can't really read the number of neighbors, right? Complex splitting. Which is why we get something called J values, or coupling constants, to tell the relationship between the alkene hydrogens, whether they are cis, trans, geminal, or alpha to each other. And he'll give you a list of different J values where you have to play like some sort of matching game. And when you match those J values together, that's how you can tell like what the relationship between the hydrogens are. Like if they're cis, trans, geminal, alpha, or allylic, right? There's also another one, but you won't probably see that in this midterm, like between 0.5 and 5. When you see a broad peak, then that's like an alcohol, or NH2 or NH because of the hydrogen bond. That's more for 118A, right? When you see a broad peak like that, you probably won't see that here in 118B. And this J value stuff here is very important, especially for this midterm coming up. So make sure to know these J values, and I will walk you guys through it right now. Okay. So we have these hydrogens here, and we have I'm going to ignore these peaks, right? Because these peaks are very crowded. And I'm going to look at this peak here between 4 to 6. And I know that these 4 hydrogens here between 4 to 6 are the alkene hydrogens, right? And that's going to be either hydrogen D, E, G, or H, right? Because those are the hydrogens on the vinylic carbon directly on the alkene. Now, he's saying that this is peak 1, peak 2, peak 3, peak 4, right? And he labeled the peaks out right here. So he already gave us the structure, which is nice. What J values would you guys expect D and E to match if they have this sort of relationship with each other? Right, let me pull out the J values for you guys again. What J values would you guys expect them to have? Around 10-ish, right? And that's gonna be 2 and 4, right? So I know 2 and 4 is either gonna be D or E. I don't know yet, right? So to figure that out, I then see they also have matching J values of 6 right here. So that means that 6 is going to be alpha. And the alpha means that this alkene hydrogen right here has a relationship with the alpha carbon hydrogen, like that. Right? And it looks like both D and E have alpha relationships with hydrogen, right? D and C are alpha to each other. E and F are alpha to each other. Like that. Right? So I'm gonna put, let's say, I don't know, like 2 and 4. It could either be D or E, but I'm gonna come back to that and come back to it later. So now let's look at 1 and 3. 1 and 3, they have a matching J value of 15, which means that they are trans to each other. And I see that my trans alkene is G and H, right? So 1 and 3 is going to be either G or H. G or H. I'm going to come back and figure out which one is which later. Okay, but does that make sense so far on how I like figured those out? Like what 1, 3, 2, 4 is? Like 2 and 4 are cis because of the matching J values of around 10. 1 and 3 are trans because of the matching J values of like around 16. Okay. Now I'm going to cross out what I did so far so I don't get confused on what I need to do now. Okay. Now, what did we say 2 and 3 was again? The region between 2 and 3 in this HNMR? Alpha, right? And we have 2 alpha positions here, and I'm gonna color code that in pink. This alpha position and that alpha position there, right? So HC and HF are gonna be between 2 to 3 in the alpha region, right? So this is gonna be either HC or HF, and both of them have 2 hydrogens, right? And that makes sense because C has 2 hydrogens, F has 2 hydrogens, like that. Now, let's read the number of neighbors. How many neighbors does this peak 5 have? 2 neighbors. Yes, because there's 3 subpeaks. Which one has 2 neighbors, C or F? F, right. And that makes this C, but we can confirm that. How many neighbors does peak 6 have? To confirm, just to confirm. One, two, three, four. 4 subpeaks, 3 neighbors. And let's check that out. 1, 2, 3 neighbors. That checks out. So peak 6 is C, right? So now I'm going to cross out C and F because I crossed that out. Now, we can do process of elimination here. We have one peak that has 2 hydrogens, and there's only one of these hydrogens that has 2 hydrogens. Is it A, B, or I? Yeah, so we know H, C, and HF are alpha carbons because they are one carbon away from my pi bond, right? That's what an alpha carbon is. One carbon away from my pi bond, either an alkene, carbonyl, or an alkyne, right? HC is one carbon away from this alkene. HF is in between these two alkenes right here, right? So HB here has 2 hydrogens. So this has to be HB, which has 1, 2, 3, 4, 5, 6 subpeaks. So that means it has 5 neighbors. Let's check that out. 1, 2, 3, 4, 5 neighbors. That's good. Making sense so far? Or am I going too fast? So now we have 2 remaining peaks left. 3H and 3H, but we have A and I that is 3H's. To tell the difference, we look at the number of neighbors. Let's look at peak 7. Peak 7 has 1 neighbor, and which one only has 1 neighbor, A or I? A or I, yes. So it's gonna be I because it has 1 neighbor here, which is whatever that is, H, yeah, H. So this is gonna be I, and that makes this is A, right? Which has 1, 2, 3, 2 neighbors, right? Because these are the 3 A hydrogens, 1, 2, 3 A hydrogens, and its 2 neighbors are these 2 HB hydrogens right there, right? And this is H NMR, so we're looking at the hydrogens. Yeah, this is not C NMR, right? Yeah. Okay. And another way that we could confirm like this is like, why is F more D-shielded than C? Like it's more to the left, more D-shielded than C, even though they're both in the alpha region, because F is in between 2 alkenes, whereas C is only like, you know, next to 1 alkene. Like F is alpha to 2 alkenes, and C is only alpha to 1 alkene. And because F is alpha to 2 alkenes, it's more D-shielded. It's more to the left. So that's another way that you could confirm this. Or if you were to like predict the product from scratch and he didn't give you this, that's how you could tell the difference between F and C. F is more D-shielded because it is alpha to 2 alkenes, whereas C is not as D-shielded as F because it's only next to 1 alkene. Like that. Okay. Now, let's see. 1, 2, 3, 4. Let's see. I'm actually not sure how to differentiate between this right here. Let me check the key of this really quick. Because like the J values are all the same. If they were like to give me different J values, then I would be able to differentiate them. But they're all the same. Okay. Yeah, so the second and fourth one, it's either D or E, but the first and third one, the first is G, and the third is H. And let's figure out why. Okay. First, third. So let me erase this. So G right here is trans to H, right? So 1 and 4, because they have matching J values of, no, 1 and 3, because they have matching J values of 15. And oh, I see here. So 1 has a triplet, which is G, because it has 2 neighbors here. 3 has a quartet, because it has 3 neighbors, and that is H. Where is H? Right here. Quintet. Okay, so that's very sneaky right there. You can't really read the number of neighbors from here, but you can read how many neighbors from this one letter right here, right? That 1T means that this is a triplet, aka 2 neighbors. This Q is a quintet, which means that there are 4 neighbors, and that's how we were able to differentiate between G and H, right? G is 1 because it has 2 neighbors, right? We can't tell the difference in the J values here because they are the same J values. In other examples that you're going to see in winter 2023 sections, you could clearly tell the difference between like these because they have different J values, especially for the alpha carbon. But this one I got stumped because they are the same J values, so I couldn't tell the difference. But the way that he told the difference here is through this peak right here to find the number of neighbors, right? So 1 had 2 neighbors, which is G, right? And if you go back to G right here, over here, G has 2 neighbors, 1 here and another one there. Whereas 3, which is H, has 4 neighbors. So if we go back to H right here, its 4 neighbors are these 3 I hydrogens and 1 G hydrogen right there. So that's very sneaky, right? So this one here does matter, like the T, the 1 letter coupling as well, right? But did we get everything else right? FCIBA, FCIBA, FCIBA. Yes, we did. Okay, that's good. Any questions on how I worked through this problem or how we got to these peaks right here? Yeah. Wouldn't it be based off of G being more de-shielded? It is closer to the other double bond. Yeah, so that is another way that you could think about it. G here is more de-shielded because it's more to the left side, whereas H is more shielded because it's more to the right side. And G here is closer to the other double bond. H is farther away from the double bond. So that is another way to look at it, right? G is more de-shielded, H is more shielded. So that's why G is more to the left side, H is more to the right side, right? Another way you can see it is this coupling constant here, right? There's a lot of like puzzle pieces that you could work with to confirm your findings. Yeah. Any questions on this spectroscopy problem, this octopus spectroscopy problem? Okay, once I'm done with spec, do you mind doing synthesis examples? Okay. I don't have the list of reactions and the reagents like I did last time, but I do have something like this though. Right, where it's a list of reactions and the check marks here are the mechanisms you need to know. And then this X2 addition, you need to know the CCl4 with water and addition of HX, X2, thermodynamic versus kinetic. Right there. Yeah. That's good. Oh yeah, mass spec. Okay. So mass spec is like conceptual multiple choice question. You're basically cutting up a fragment. So let's do it here. Mass spec. You're cutting up a fragment, and in this case, we'll talk about alkynes. And then the most stable fragment, the major fragment, is going to be the one with the papardrylic. Papardrylic. Carbocation, because it could do resonance. So I'm not too familiar with mass spec, how he's going to ask it, but know that there's different ways to cut up a fragment. Like this one with alcohol, this one with alkenes. And let's say if you had an alkene like this, the major fragment would have the carbocation at the allylic position, right? Because it could do resonance like that. For alcohols, that would be like a positive charge underneath the alcohol oxygen right there. And there's a name for that, like alcohol defragmentation or something like that. And you have to know the names of how each functional group, alkyne, alkene, and alcohol, fragments in the mass spectrometry, right? But I'm not too familiar with that mass spec stuff. Yes, I will drop the PDF tonight on the Discord and the school website. Yeah. But look through his exams that I just sent you, winter 23 and winter 24 for sure, and see how he asks mass spec stuff, and start making patterns notes on like what he tends to test stuff on the mass spec. Yeah, and I need to review mass spec myself. Like I don't know too much about mass spec because I was never taught it in 118B. I had a different professor. Yeah, someone who struggles with synthesis. What is your best advice tip on how to get synthesis questions? I'm kind of getting there, but still pretty hard. Yeah, of course. Yeah, so it's a lot of retrosynthesis going backwards, knowing the reactions like very well, like the transformations. A tip that I have for you guys on the exam, during the exam, is that when you guys get stuck on the synthesis problem, go back to the predicted product section, right? Where there's like the reactant and the reagent, and there's boxes for you to write out the products. Those reactions, like in the reagents, could give you a hint on what's the reactions on the synthesis. So if you guys have no idea on what reactions to do and you guys get stuck in the middle, right, then go back to your note card or the reactions from the predicted product. So that might help. Yeah, that hurts. Okay, before we end up the session, I want to do two more things. I want to do the kinetic versus thermodynamic product, and then I want to end up with synthesis problems. So let's do that. Okay. Yeah. So let me give you guys my step-by-step process on what I think about when I think about kinetic versus thermodynamic stuff. So the kinetic product will come from the most stable intermediate. Right? And there's different types of intermediates. There's carbocation intermediate, there's radical intermediate, and there's anion intermediate. But in this specific set of reactions, when you specifically, you guys are being tested on conjugated diene addition of HX and addition of X2. The intermediate is going to be a carbocation, right? Intermediate is a carbocation. With the NBS example that we worked with earlier, the intermediate was a radical. The thermodynamic product is gonna make the most stable product, right? And it's gonna be different products for different reactions, but for the reactions that you guys are being tested on this midterm, is an alkene. Right? So when you think about kinetic, most stable intermediate, think about most stable carbocation. When you think about kinetic, most stable product, most stable alkene, most substituted alkene. Okay. And kinetic is the one that gets formed first, very fast. And this is favored in low temperature, right? Which is going to be less than 40 degrees Celsius. Thermodynamic is going to be favored in high temperature, which is greater than or equal to 40 degrees Celsius. Helix tends to use 0 degrees for kinetic and 60 degrees for thermodynamic, but in some of his practice exams, he used 55 at one point. So I'm giving you guys this so you guys don't get tripped up when you guys see a different number other than 0 and 60. Right. Okay. So now here's my step-by-step process on what I think about when I do these types of problems. It takes like 4 to 5 steps here. The first step is to form most stable carbocation on both alkenes, right? Because we're working with conjugated dienes here. There's 2 alkenes that are conjugated. And when we're adding HX or X2 to it, one equivalent, then there's 2 alkenes to work with. We're going to react with both alkenes and form the most stable carbocation there. And there's a tricky part to this, right? And I'll show you guys when I go over examples. The next thing is to draw resonance sets for both alkenes. Resonance sets, right? And then the third step is to pick or choose the best resonance set with the most stable carbocation intermediates. choose the best resonance set. Okay, and then once you pick the best resonance set, then you choose the intermediate based on the temperature, right? Kinetic intermediate or thermodynamic intermediate based on temperature. Now I'm gonna write in green the tricky example that he included, which I will go over with you guys after we go over simple examples first. So for thermodynamic, you can have more than one thermodynamic products. If you have equally substituted alkenes, equally stable alkenes, you can have multiple products for thermodynamic. For kinetic, since you're looking for the most stable carbocation, if there's a tie between the carbocations, choose the first one that gets formed, because we're thinking about speed here. We wanted the first product that gets formed. Choose first carbocation that gets formed. Right, so a lot of this might be mumbo jumbo for you guys right now, like a lot of vague stuff, but it's gonna make more sense when we do practice with this. So let's do that now, and then we can refer back to this. But this is basically what I think about when I work through these problems here. Okay, let's do this one here. Let's do this conjugated diene reacting with 1 equivalent of HBr, and I'm gonna put 0 degrees Celsius in green and 60 degrees Celsius in blue, because we're gonna practice with both here. So now let's work with both alkenes. If I work with this alkene here and I do HBr, I'm gonna protonate it and give us my more stable carbocation intermediate right here. Once I have that, then I'm gonna draw its resonance structure, right? To get that first resonance set. Okay, now that's the first resonance set reacting with the alkene on the right. Now, if I react with the alkene on the left, form the more stable carbocation intermediate. Draw out its resonance structure to get that second resonance set. Now we have 2 resonance sets, but we're not going to work with both. We're going to choose one. And to do that, let's analyze what carbocations we have. This is a secondary allylic carbocation. This is a primary allylic carbocation. This is a primary allylic carbocation. This is a tertiary allylic carbocation. Allylic meaning that it's 1 carbon away from the carbocation, alpha to the carbocation. Now, we see that primary and primary cancels out. They're the same. Tertiary versus secondary, tertiary wins. So I'm going to completely ignore the top resonance structure and then think about this bottom resonance structure here, right? Now, let's also analyze the alkene. This is a mono-substituted alkene. This is a tri-substituted alkene. Now, which one would you guys say is the kinetic intermediate, and which one would you guys say is the thermodynamic intermediate? A or B? Or first is kinetic. Kinetic is A, right? Thermo is B, right? Yes, that's correct. Okay. Because kinetic, we're looking for the most stable intermediate, which is this tertiary allylic one. And then thermodynamic, we're looking for the most stable alkene, which is that tri-substituted one. And Emily, there isn't a key, but after the session, before I send the notes, I'll just quickly put in the products key before I send out the notes for you to check your answers. So you can think about 1-2 or 1-4 addition, but I don't like thinking about that, right? I like thinking about how kinetic comes from the most stable intermediate, thermodynamic comes from the most stable product, because thermodynamic can be both 1-2 and 1-4, and kinetic can be, for Helix class, only 1-2. Yes, so usually thermodynamic is 1-4, but not always the case. It could sometimes be 1-2. That's why I don't like thinking about 1-2, 1-4 addition. I like thinking it like this to get the right answer 100%. Right. Yeah, hopscotch. Okay, so now the Br minus that got kicked out is just gonna attack those carbocations and give us our products. If we were given 0 degrees Celsius in green, our kinetic product, like you guys said, is A, where the bromine attaches there. Our thermodynamic product is this, when the bromine attaches here, right? Thermodynamic, more stable alkene. Kinetic came from the more stable carbocation intermediate, right? And only draw out one of the products depending on what temperature you have. If you're only given 0 degrees Celsius, this is your only answer. If you're given 60 degrees Celsius, this is your only answer. For this example, there's gonna be some examples where you have multiple thermodynamic products, right? Okay. Let's make this a little bit harder. And this time let's do X2. Both in kinetic and thermodynamic. Okay, so for this one here, now what's the intermediate here? Let's work with this alkene here. What is that special intermediate when we react this alkene with Cl2? Ring, yes. Chloronium ring, halonium ring, like this. And what is the next step you guys predict is gonna happen? We have Cl minus floating around. What is the next step here? What do you guys think is gonna happen? This is very different than what we learned about this reaction. Yeah, so when we learned about this reaction, the Cl minus attacks the ring and breaks open the ring like that, right? That's when we have a regular alkene. But because this is a conjugated diene, think of this as a very good leaving group, and we could form a very stable carbocation, either here or here. Which position do you guys think is going to form a very stable carbocation? Think of this as an SN1 reaction now, where the leaving group is just going to leave by itself first to form the more stable carbocation intermediate. B, right? Because it is at the allylic position. That's the term that I want you guys to know and like stick to your mind when you guys are doing these reactions. Allylic position, right? Because that's gonna be very important. Now we're just gonna break open that ring and form this allylic carbocation here. Cl, positive charge. Now we could continue with the resonance set like this. Don't forget the Cl there. Boom. Okay, let's do this one. Same thing. Okay. Break open the ring that way to form the more stable allylic carbocation. Resonance set. Okay, now also have a two resonance set. Let's analyze our carbocations. This is a secondary allylic carbocation. This is a secondary allylic carbocation. This is a secondary allylic carbocation. And this is a tertiary allylic carbocation. Which resonance set do you guys want to pick and choose to keep? Yeah, the second one, bottom one, pink one. Yes, get rid of this top one, blue one. Because tertiary allylic beats secondary allylic. Okay, now let's analyze the alkene. This is disubstituted, this is trisubstituted. Which one is your kinetic intermediate? Which one is your thermodynamic intermediate? First is kinetic, right? Because it has the more stable carbocation intermediate. And then second is the thermodynamic because that's the more stable double bond, right? So Cl minus attacks to get both products. If you're given 0 degrees Celsius, you're gonna get this kinetic product. If you're given 60 degrees Celsius, you're gonna get this thermodynamic product. Just like that. Right. Okay. Now let's do So Cl minus, is it the reason why we opened the three-membered ring? Yes. In previous reactions with alkenes and alkynes, whenever we form the halonium ion ring, the Cl minus usually breaks open the ring by attacking it, but not in this case, because in this case, we have a very stable carbocation that can be formed. When you have a conjugated diene like this, and you can have a very stable carbocation that get formed, like the allylic carbocation, right? Then it's going to act as an SN1 reaction. The leaving group here is just going to leave by itself first, right? It's like so excited, so eager to leave to form that that allylic carbocation right there, right? So instead of the CO minus attacking, it's going to leave by itself first, do resonance structures, and then this is when we choose the best resonance structure, and then the CO minus attacks the carbocation, whatever, depending on what temperature we're in, right? Low temperature for kinetic, high temperature for thermodynamic. Yeah. Okay. Now, let me give you guys two more difficult ones here that are going to use these green notes here. So far, we did the notes here, but now let's do the interesting ones here, the weird ones. Let's do... the one that Helix gave in class was something like this. Right, let's do that one first, and then I'll make one up that's similar to that. 1 EQ HBr. Let's do both 0 degrees Celsius and 60 degrees Celsius. Okay, now let's react with both alkenes here. HBr, attack, kick out. Oh wait, what am I doing? This is not X2. We protonate the alkene, form the positive charge here, get the resonance structure. Right, that's our first resonance set. Right. Okay, now let's react with the other alkene. Now, both of these carbonates are equally substituted, but which one is more stable, A or B? Which carbocation do we want? Carbocation at A or carbocation at B? B, right, because it is at the allylic position. So we're gonna attack the hydrogen using that carbon, kick out the chlorine, and get the carbocation at B, because it can do resonance with the ring, I mean with the double bond, to give us this resonance set here. Okay, now let's analyze the carbocations. Secondary allylic, secondary allylic, primary allylic, secondary allylic. Which one do you guys want to keep? First one, top one, blue one, yes. Okay, let's analyze the alkene. Di-substituted, di-substituted. Okay, what do you guys notice here? What's the problem here? What is the problem? Like, what is the thermodynamic product? What is the kinetic product? If you have a tie like this, they're equally substituted, right? So if we're looking for the thermodynamic product, let's say, how many products would we get? Would both of them count as a major product if we're going for the thermodynamic product, or would only one of them count for thermodynamic? Thermo. So yes, both for thermo. So if you're given 60 degrees Celsius, you're gonna get two products, right? That product and this product here, right? For thermo product. Thermo, you could get more than one, right? Can have more than one products, multiple products. But for kinetic, if there's a tie between the carbocations, choose the first carbocation that gets formed to get the major product. So if we go back here, which one would be our kinetic intermediate? A or B? A, right? Because A is the first one that gets formed, right? It takes time to move those electrons of that bond to go over to make a bond over there, and we don't like that. Kinetics doesn't like that, right? Kinetics wants to form the very first thing very fast from the more stable carbocation. So for kinetic product, we only get one product, which is that one right there. Right? So 1 kinetic product, 2 thermodynamic products, like that. Any questions on this tricky example here that Helix gave in class? This is the one that he gave exactly in class, but he did it with like kinetic product. Oh, he did both actually. Any questions on this one? Okay, now I'm gonna give you guys this one to practice with, right? And I am going to get a water break, and we're gonna finish off the session with synthesis problems. And give me both the kinetic product in green and thermodynamic product in blue, just for practice. And notice here, this is not HX. This is this is X2, right? And it's different, right? X2 is going to be harder because of the extra step where we have to like break open the ring by itself first to form the carbocation, right? And in HX, we get the carbocation right away when we protonate the alkene. But X2, when we form the ring, we have to form the carbocation by breaking up the ring first, like that. Okay. Okay. Oh, wait, before you guys try that out, I want to go over this with you guys really quick about the allylic position. So you know how we talked about carbocation stability? Methyl is like the least stable carbocation, and then primary, and then secondary, and then tertiary. There's something more stable than tertiary carbocation, right? Which is a secondary allylic carbocation. And something more stable than a secondary allylic carbocation is a tertiary allylic carbocation. So keep that in mind when you're like trying to determine what's the more stable carbocation, right? Choose the carbocation that is allylic and can do resonance, right? Because for example, let's say you have, let me just give you this random ring right here. No, actually, no. Let me give you something like this. And we react this with 1 EQ HBr. If we look at this alkene right here, right? Where would the carbocation be more stable at? A or B? This is a little bit tricky one because this kind of goes against what you guys have been learning, right? About carbocation stability. But there's a new factor here. Which one is going to be more stable for the carbocation? A. Yes. Even though A is less substituted, right? Like if I were to draw you guys out the carbocation here in A, that is secondary, versus if I drew you guys out the carbocation here, that is tertiary, right? This is a tertiary carbocation, right? But this carbocation here is secondary, allylic. And this allylic thing allows for resonance, which increases the stability. Resonance is a stabilizing factor. So even though this looks less substituted than this one is more stable because it is allylic. And that's why this allylic position is very important because it allows for resonance. Okay. So when you're making your carbocations, keep in mind of this allylic position here that can do resonance with the other double bond. Okay, now you guys can try this. Yeah, because of delocalization. Okay, when you guys are ready, you guys can send me a picture of what you guys got, or someone can try explaining to me if you guys feel comfortable, or if, I can walk through this with you guys. Yeah, you guys need more time on this one? Okay, let's see. So for this one, yeah, it's okay. Form the bromonium ion ring. Oh, okay, those were your products. Okay, I see. I was trying to see the mechanism, but you gave the products. Okay, let's see. So this is your kinetic. Okay, kinetic, thermal. There's two that you gave. One here. And another here. Okay. So let us walk through this. Let's see. Yeah. Oh, okay. Yeah. Okay. Let's see. Nice work. BR. Kick out the BR. Make that bromonium ring. Now, when we kick off this ring by itself, like SN2 reaction, this one looks like the more stable carbocation because it's more substituted, right? But it's actually not the more stable carbocation. We're gonna kick off this ring to form this carbocation that is less substituted, but is allylic. And that allylic property makes it more stable. So we're gonna kick off the leaving group that way and give us this carbocation here that is allylic. We're almost done, guys. After this, we're just gonna do 6 synthesis realms from easy to hard. BR positive, right? And then get that resonance set. BR positive. That's that resonance set right there. Now let's do the same with the other alkene. Form that bromonium ring. Yeah, ingrain allylic in your brain. Tattoo allylic in your brain. Yes. Did you kick out the carbocation on the other side, Khadija? Did you make a carbocation here at the tertiary position? Oh my God! You didn't know about the allylic position until now? That's crazy. Allylic is like the most important thing here. Oh my God, that's okay because all the tutees that I tutored, right? When I asked them which is the more stable carbocation that's gonna get formed, at the first time they all said that as well, right? Because it's more substituted. So that's like a very common mistake. Yeah. So don't worry. But now, tattoo this in your brain for the exam. Allylic. Very important. Right there. Okay. Right, because if you form a carbocation here at the tertiary position, that's not able to do resonance with alkene at all. Like there's an sp3 roadblock right there. So this alkene like can't make resonance with this carbocation at all. Like you would just stop there. Right? But we want to make resonance forms with the allylic position. Okay. BR plus. Right? Now this one here it makes sense because it's more substituted and it's allylic, so it kind of like matches with what we've been taught. Right, but this is the new thing. Allylic secondary carbocation more stable than a regular tertiary carbocation because of resonance. Right? Okay. So Br, positive charge, alkene, get that resonance structure in. Get this resonance set. All these rings. Okay, positive charge. Now let's analyze the carbocations. Secondary allylic. Secondary allylic. Put that in your note card, like the allylic. Like put it in big bold words, big capital letters, highlight it, underscore it, underline it, put a red star on it. Tertiary allylic. Pick the bottom one. That's the most stable one. This is tri-substituted alkene and tri-substituted alkene, right? So now there's a tie between the carbocations and there's a tie between the substituted alkenes. And so we said if we're looking for the thermodynamic product, both would work. So in blue, both right here is the thermal product. Right? Now for the kinetic product in green, we choose the first one. Ignore the second one because it takes time to get there. It takes time to get this resonance structure, and we don't have that for kinetics. Right? Kinetics, we get the first one that gets formed. If there's a tie between carbocation intermediates, which is this right here, kinetic. Okay, now let me teach you guys the 1, 2, 1, 4 addition stuff, just in case he tested a multiple choice explanation question or multiple choice question, because I don't use that when I do these types of problems. But let me show you guys just in case he puts it in multiple choice or explanation. So the 1 comes from the first atom that gets attached. It could be Br or hydrogen, right? Depending on what reagent you have. If you have X2, then halogen is going to be added first. If you have HX, then hydrogen is going to be added first. So that's going to be your atom number 1, right? Atom number 1. And now just keep that in mind, right? Because if you look at the product here, that's atom number 1, atom number 1, atom number 1. Then if you count to the next atom being attached, then that's going to be showing what addition you had, right? So these two products here, 1, 2 addition, 1, 2 addition. This one here is 1, 4 addition because the relationship between these two groups are 1, 4 from each other. So the kinetic here is 1, 2 addition. Thermodynamic can be both 1, 4 or 1, 2 addition. Right, so that's the 1, 2, 1, 4 addition stuff for conceptual question or like explanation question. Okay, so let's check that with this key right here, or that Sharon tried. Nice. This one is this one. Nice. Yeah, you got it. Nice job. Yay. Any questions on this one? Okay, so now let's level up with synthesis problems and this session off with synthesis. Do you guys include stereochem with this? There are character centers being formed here. And there can be stereocenters. Huh. What does Helix's key say, like, for his package sounds? Because, like, you technically can. Like, this could be wedge. This could be wedge. There's 4. Oh, yeah. You would say 4 stereoisomers. I remember. Stereoisomers. Right? And the 4 you could put that in the answer key. Right? And the 4 stereoisomers are these. Right? Both of these bonds here could be wedge. That's 1 stereoisomer. Both of these bonds could be dashes. That's another stereoisomer. This bond could be wedge. This bond could be dash. That's the 3rd stereoisomer. And the last stereoisomer is this bond could be dash. This one could be wedge. Like that. So if you just put this, then you get full credit. Yeah, nice question, Yasmin. So if you see this, put 4 stereoisomers. If you have 2 x's like that, right? That's only if you have addition of x2. If you have addition of hx, then you won't have that bromine. You would have like a hydrogen there. Then you would put like plus or minus for the enantiomer. Yeah. For kinetic and thermodynamic, these ones as well. 4 stereoisomers for this and 4 stereoisomers for this as well. Yeah. Well, be careful here. We could put for this one, it actually depends, right? This is 4 stereoisomers because we have 2 chiral centers. But is this a chiral center here? No. There's 2 methyl groups. Right? So we can't say 4 stereoisomers. There's actually 2 enantiomers. 1 wedge there, 1 dash here. So we could put plus minus. right? So stereochemistry, from what I've seen, it can be tricky here. So you just gotta be careful with what your chiral centers are and where they came from, like a carbocation or radical or backside attack from SN2, right? So 4-star estimates for this, yes. 4-star estimates for this, yes, because we have two chiral centers that could be like different, and we only have one chiral center here that changes. So plus minus, right there. Okay, that was a good question. Always look for stereoisomers chiral centers with anything that forms a carbocation. Yes. Carbocation or radical, like with NBS, HBr ROR, or sodium metal reduction, right? Like with the like those things. Yeah. Okay, you guys ready for synthesis? Let's start with the baby synthesis, one-step synthesis. Let's start off and level up as you guys level up here. Let's fight this little baby goblin. And end off the session here. Okay. Let me know what reaction would convert that alkyne into this trans alkene. Yeah, Na metal with NH3 liquid, dissolving metal reduction, right? This is one of the reduction reactions with like H2PDC all the way down to alkane. H2 Linois catalyst, get the cis alkene. This one, dissolving metal reduction, get the trans alkene. Nice. Okay, let's go make it a little harder. Now, let's say that we have this structure and we want to convert it to this structure here. There we go. Okay, this is gonna be easy for now. And we're gonna increase the difficulty as you guys get these right. And then 6 of them. So it looks like there's a Grignard reagent going on here, right? Because we're adding a carbon-carbon bond. But think of an alkyl anion as a Grignard reagent equivalent, right? Where this carbon right here is going to be my star carbon. This is going to be my dot carbon. And this is the new bond that gets formed between them. So let's make that disconnection right there and go backwards, right? How can we make this carbon here negatively charged, right? This terminal alkyne here negatively charged. There's 4 bases we could use. Yeah, I see NaH, NaNH2, LDA, and lithium. Any of those 4 bases that we talked about earlier, right, can deprotonate that terminal alkyne hydrogen to make it negatively charged, right? Now, once we have this negative charge thing, then we got to do SN2 reaction with CH3, CH2Br, right? Because that's a star carbon, and I'm going to draw that dot carbon out like that, right? With that ethyl group sticking out of it, that decoration. And then to make it electrophilic with a good leaving group, we could put bromine there for SN2. Like that. 2 steps. First step, acid base. Second step, SN2. Yeah. Okay, nice. Let's move on to the third one. Let's do this one here. No, I don't want to do that. Yeah. Yeah, I'm just looking through my previous session notes that I made with these alkene reactions. So let's do this one here. This one here. There we go. And the next one would be this. So let's do Br2 CCl4, not water or alcohol, because we want to get a vicinal dihalide, right? So equivalent NH2, Br2 CH3 CH2. Yes, you guys got it right. those are the right answers, but let me explain how to think about it for people watching or stuck on this one. So I'm highlighting my similarities here. That's the yellow highlighted part right there. I'm gonna say that this alkyl carbon was the nucleophile, this was the electrophile, that was the new bond being made. So I'm gonna make a disconnection right there, right? So I'm gonna go backwards here. I'm gonna say that that alkyne had a negative charge, and then to attach that group attached to it, that's my dot carbon with a good leaving group, bromine right there. SN2 reaction. Attack that carbon, kick out the leaving group. Now, to get to here, the ways that we can make an alkyne is from a vicinal dihalide when we have two halogens adjacent or vicinal to each other, right? Like that. And to get to this terminal alkyne with a negative charge, we could use NaNH2, at least 3 equivalents. We could say excess, right? First equivalent to make the alkene, second equivalent to make the alkyne, and then third equivalent to deprotonate that hydrogen to create this negative charge right there. And I'm not doing acid workup here because I don't want the neutral alkyne. I want to keep that negative charge alkynyl anion to do this SN2 reaction here. Now to convert this alkene into this vicinal dihalide, I do the alkene reaction with Br2, CCl4. So the first reaction here is halogenation. Second reaction here is E2 2 times. And then the third one is acid-base reaction to get to this alkynyl anion. And then we do SN2 here. Right. Any questions on how I got this synthesis problem here? Okay. Okay, let's get a little bit more interesting. Okay, let's try this one. How does it form the extra bond? Yeah, it forms the extra bond by doing SN2 reaction. If I highlight this pair of electrons here in red, like that, and that attacks this carbon right here and kicks out the bromine, that's this new red bond right there. And if I highlight this substrate electrophile in pink right there, that's the substrate electrophile in pink right there. And Br minus gets kicked out as a SN2 side product reaction, like that, right? And this right here was the yellow molecule, right? This red pair of electrons is that new red bond right there, right? Which this is the nucleophile, attacks the electrophile, kick out the leaving group, attach those two pieces together, like that. Okay. Okay. I'm just gonna write it all out here. I know I said 6, but I want to try this challenging one, this boss battle one. This boss battle one that is gonna have some 118A reactions in there. And then we will be finished. Okay. So let me walk you guys through this. We have an aldehyde right here. If I highlight my original molecule in yellow like that, that's my original molecule in yellow like that. The differences are going to be this bromine and aldehyde right there. Now, let's think about this. There's actually two ways that we could do this here. There's the Midterm one way where we don't have to use any alkyne reactions at all, and there's the one where, like, you know, we just we do the alkyne reaction. So thinking about it backwards here, where do you think this aldehyde came from? There's two ways actually. Number 4, tautomerization. Yeah, so that's one way. Yes. So Lydia, LDA, HGOAC, NABH4, PCC. So when you do, oh shoot, yeah, LDA like that, right? And then you do oxymergration demercuration, you get that ketone. And then when you reduce that with NABH4, you're gonna get this alcohol right here. And then when you PCC it, you're gonna go backwards to the carbonyl right there, right? So, that is very close to the first reaction, but tautomerization from CY to BH. So that's one way, right? So now that is going to, let's say, come from this alkyne right here, and we do tautomerization of alkyne with CY2, BH, THF, second step, H2O2, NaOH, water. Okay, now how could we form a terminal alkyne again? Like what reagents form the terminal alkyne from, let's say, vicinal dihalide, like we said earlier? What reagents? A neutral terminal alkyne. How many equivalents of NaNH2 do we need? At least 3, right? Not 2, because 2 would be for internal alkyne. We need at least 3 NaNH2 for terminal alkyne. But to be safe, if you guys don't want to remember that, just put excess for synthesis, and you get full points, right? Like that. Right? Okay. Now, where did this vicinal dihalide came from? Like, let's say, like these 2 carbons here that hold the 2 bromines came from an alkene. Like what reagents? So HBr would add bromine to the Markovnikov side, right? If you had HBr, this would be the product. Like instead of bromine here, you have hydrogen here. We only add 1 bromine to the Markovnikov side, right? So Br2 and water. If we put Br2 and water, we have a competing nucleophile, water. So we would have OH at the Markovnikov side. So tert butoxide would convert this into this terminal alkene right here, right? Like tert butoxide or LDA would do E2 Hoffman to convert this reactant molecule into this less stable, less substituted Hoffman alkene. But the reagent that can convert this alkene into this vicinal dihalide is, does someone have it? Someone know it? Very close to Br2, H2O. But instead of H2O, what if we don't want OH here or OR there? CCl4. A product solvent, CCl4. Yes. Because if we have water, that would put OH on the Markovnikov side. But we want to put 2 bromines on there, like that. Right. Okay. So the first reaction we did was E2 Hoffman to create the less stable alkene. Second reaction we did was halogenation in a product solvent to put 2 bromines on the alkene like that, vicinal to each other. And then we created a neutral terminal alkyne. And then we did hydroversion oxidation to get this aldehyde right here, right? But the intermediate was like this, because we know that this is an anti-mark addition. So we're going to have alcohol at the lesser position right here because of the water, right? But why don't we stop here? What is this functional group? Why don't we stop there? Enol, yes. And that enol will do tautomerization in acidic conditions or basic conditions, if this was mechanism. Basic conditions, because we have NaOH and water. Basic conditions. It's okay. It's okay. It's late. It's late. Okay. So let's try this one out. Let's say that came. Well, actually, let me show you guys the other way, which is probably the quicker way, the midterm 1 way, because I know some people that are gonna watch this video are gonna be, like asking why can't we do this way, which is the faster way, and it is, and I'm gonna show that way right now. Okay, so one way that we could do this, the shorter way, is LDA or terbutoxide to create that terminal alkene, and then from here we could do hydroversion oxidation to get the alcohol. at the left subside, right? With H2O2, NaOH, water. Get the alcohol right there. And then from this alcohol, we can PCC that primary alcohol into the aldehyde right there. Much faster, much higher yield, much more efficient synthesis. So this was midterm 1 reactions, right? 118A, 118A, 118B, midterm 1. Yeah. But you guys were like in the mindset of the midterm 2 reactions already, which is good practice, which is going to probably show up for the midterm reactions. So that's good. Okay, let's move on to the next one. Okay. So let's work backwards here. What do you think you get this carbonyl came from? Like what reaction? Tautomerization, yes. In the intermediate, right? Let's say there was an enol right there, like an OH here, and then an alkene right there. And the reason why I'm putting the alkene right here instead of right here is because we see the vicinal dihalide right there. So it's easier to put the alkene right there, right? But what came before that was an alkyne. So let's put an alkyne right there. Boom, 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 boom. Now, what reaction would put an alcohol at the Markovnikov position of the alkyne? What kind of reaction? If you go backwards even further. HgSO4, H2SO4, and water. Yes. And when we do tautomerization, what conditions would we do it in now? Acidic or basic conditions when we tautomerize this? Acidic conditions, right? Because we have H2SO4, strong sulfuric acid. Nice. Okay, now you guys complete this off for me. How can we form this terminal alkyne from this vicinal dihalide? What sequence of reactions would we have to do? Yes. First, NH2 minus 2 times, or at least 3 times, right? Let's put excess. And then since we want the neutral one, acid workup, H3O plus. Like that, 3 times. All right. Okay. Okay, this one here. We went over this reaction earlier in the session. What do you guys recognize about, let me color code the original molecule, which is this one here. What do you guys recognize about the relationship between this bromine and carbonyl here? So it is alpha and allylic to the carbonyl right here, right? But NBS creates a bromine allylic to an alkene, a carbon double bond carbon. This is not a carbon double bond carbon. This is a carbon double bond oxygen. This is a carbonyl. Carbonyl, right? So this is a little bit tricky one. So let's think about this backwards again. Yeah, Br2 with what? With H2O. Yes, because if you think about it backwards here, let's say this carbonyl came from oxygen and the alkene right there, right? And they tautomized it to this carbonyl. Yes, this was the reaction we went over earlier. So that means that our alkyne must have looked like that, and we reacted with Br2, LiBr. It's probably safer to put it like that to get the full points. LiBr and water, right? And that would put, you know, alcohol on the more sub position and Br at the lesser position, just like that. But we don't stop here because we have an enol that will tautomerize into that carbonyl right there. Okay. Now, here's this more midterm 1 reaction at the beginning. What can we do to create this alkyne from this alkene right here? For synthesis, no, don't. That's a good question. Thank you for pointing that out. You don't have to put this enol for synthesis. I'm just drawing it out just to make it more sense on like where it came from, so you guys have a retrosynthesis mindset of like where that came from. But if you draw out the synthesis, this is all you need to do. Go for going backwards, right? You don't have to draw out that enol intermediate. Don't do that, right? I'm just drawing it out to help you guys think about this. Lindlar catalyst. So Lindlar catalyst would create a cis alkene from a alkyne, but this is not internal, so we can't have a cis or trans alkene. Right? let's go backwards even further. What is a way that we formed a terminal alkyne? Like if you get stuck, like try going backwards even further. Like how can we create this terminal alkyne here? Dihalide. It came from a dihalide. Yes. So let's create that dihalide like that. And NaNH2 excess. Second step, acid workup from this vicinal dihalide, from this carbon and that carbon right there. Now, where did this vicinal dihalide come from? Let's go backwards even more. An alkene, yes. So let's put the alkene right there. Okay. Now, do you guys sense something very deja vu-y? Crawling a more stable alkene to a less stable alkene? Midterm 1 reactions? Like, what reactions can we do that in? So, Yasmin, you're thinking of it isomerization going backwards, right? You're thinking of H2SO4 heat, which would convert this less stable alkene to the more stable alkene, but that's gonna go the wrong direction. We wanna go to this direction here, right? So when you guys do retrosynthesis, right, like it's going backwards, not forward, right? So don't think about like trying to get from here to here, right? We're trying to go backwards, like we're trying to get from here to here when we do this synthesis problem. Yes. What sound does a lion make? HBR, roar, roar. Right, this roar guy with the anti-mark. Right, which will put bromine at the less sub position, anti-mark position. And then we want to make that less stable alkene with LDA, bulky base or turbid oxide. Yeah, nice. So be careful when you guys do synthesis, right? When you guys are going backwards, you guys are not trying to create that from here. Like you guys are not trying to create the reactant from this. When you guys are going backwards, you guys are trying to like, see the reactions that what could have made that, 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 and that would help you so much for like going forward now, right? But don't get confused. Like we're not trying to create this. We're trying to go backwards. We're trying to create these from that reactant molecule right there, right? So this one, high radical addition of HBr, E2 Hoffman, halogenation in a product solvent, Br2 CCl4, 2, 3, terminal alkyne formation, and then halogenation in water with tautomization. So 1, 2, 3, 4, 5 steps like that. Okay. Nice. Let's do the boss battle now. Last one. To convert the alkane to alkyne, could we have used NBS? No, NBS would not convert the alkene to alkyne. NBS would add bromine on the allylic position, right? But that's the first product. You would have to first draw out the radical at the allylic position and then draw out the resonance of that radical, allylic radical, to get the other resonance structure, and then attach bromines to those radicals to get the product. The alkene will stay there, right? Yeah. We try to avoid radicals in these cases. Or these are synthesis problems. It depends, like what you want. Like if you want allylic bromines, with like carbon bond alkene, then you might want to use NBS, but probably not the case. Probably not the case, right? Because NBS would give you multiple products, and he would have to put multiple products on the product. So you probably not get NBS under synthesis. It's more for predicted products, and conceptual question, multiple choice. Yeah. Okay. So where did this carbonyl come from? Where do you guys think this carbonyl come from? This is gonna be 118A reaction. I'll give you guys a hint. 118A reaction. Epoxide, yes. Oh my god. Because this cis alkene, where did this cis alkene come from? If I highlight the original molecule like that, that's this original molecule right here. And this is the new structure here. Oh, are you saying E2 reaction to create this alkene like that? if we create an alkene right here, how can we add this group right here? Like what reaction can we do then? Yeah. Oh, so you're thinking of NH2 minus 3 equivalent of that? This is a strong base that's going to look for a good leaving group to do E2. There's no good leaving group here, so we can't do E2 here. Right. So this is going to be epoxide ring opening. And when we open up epoxides, right, the functional group we have is an alcohol. So that carbonyl there was an alcohol. And in 118A, what reaction converts a secondary alcohol into a ketone? PCC or Jones, doesn't matter, right? An oxidizing agent like PCC or Jones, right? Now, what kind of alkene is this? Cis. And what reagents can create a cis alkene from an alkyne? H2 linolyse, yes. So let's put that H2 linolyse catalyst right there. And let's put that into an alkyne like that. OH right there. Okay, so now if I were to highlight this right here still, I see that this is my original structure, the alkyne. This is the new bond right here, right? And this is the epoxide right here, right? Like this was my starred carbon. This is my dot carbon. This is the new bond between them. So if I go backwards right here, I know that I had a negatively charged alkynyl anion right there. And I did an epoxide ring opening like this. Second step, acid workup. Right, where this alkynyl anion here is the star, this epoxide carbon here, the less subcarbon, is the dot because we attack the less subside in basic conditions. Break that open, and if I want to color code this carbon in green, that's that green carbon right there. That is still attached to that oxygen right there. And then it becomes OH by H2O+. And then from here, we do LDA to create the less stable alkene, and then Br2, CCl4 to get the vicinal dihalide. And then we do NH2 minus excess to get to this alkynyl anion there. Right. So A2 Hoffman, halogenation in aprotic solvent, terminal alkynyl anion formation. And then from that, we could do 3 different reactions, SN2, E2, or epoxide opening. We did epoxide opening here to get to this intermediate. And then we did H2 linolyse catalyst to get the cis alkene. And then we did PCC to oxidize the secondary alcohol to the ketone. So there were many 118A reactions here. Right? LDA, epoxide ring opening, but that's kind of connected to this one, and PCC. Yeah. All right. Any questions on this one, guys? No? Okay, that's good. That's good. Who has the exam tomorrow? Yeah, of course. You? Oh my gosh. Oh my gosh. Are you guys gonna study more like now? Are you guys gonna go sleep or what's the plan? What's the move? Sleep? Yeah, sleep. We gotta sleep. That's good. Especially do the exams that I sent you on the Zoom chat. Like those ones I sent you guys, it's very similar. So yeah, that's good. Making an alkyde. That's good. Yeah. Okay. Well, good luck, guys. Let me know how it goes. And yeah, you guys got this. Yeah. Yeah, I appreciate it. Yeah. Thank you. Good night.